the origin. Okay, so what is the equation of that circle? The equation is x squared plus y squared is equal to r squared. So I can solve here for x, and I can say that x squared is r squared minus y squared. Now I take square root of both sides and get x is plus or minus square root of r squared minus y squared.
This is gonna be
so what is then that? There are two semicircles. This one is x is equal to minus, so this is your x-axis, this is your y-axis. X is minus r squared minus y squared, and the other semicircle so this is the other semicircle, so the whole thing is a circle, has equation with a plus in front of the square root. X is r squared minus y squared. So these two are drawn separately. The positive root is in the right semicircle, the negative root is the left semicircle, so both combined together give you this. So you can see that circle as an x simple region, because this is the region between the curve, which is the boundary of the left semicircle, and the curve which is the boundary of the right semicircle. Alternatively, we can solve here for y.
But why would
So
you
when
do that?
take square root, you get y is plus or minus square root of r squared minus x squared. So let me plot here.
So fucking dull.
So what we have is again two semicircles.
Oh yes, two
One is in the
semicircles
upper
make
half
one
plane.
circle.
Like that. The other one is in the lower, like this. This one, so this is the x-axis, this is the y-axis. This one here, the semicircle, the yellow one, has equation y is equal to minus r squared minus x squared, and the upper semicircle has equation y is equal to plus the root r squared minus x squared. Now we'll encounter this example more than once, in the future. So pay particular attention to it. So there are two parameterizations, A and B, of the circle at center at the origin and radius r. So you can view that either as a y simple region, because this is between two curves. This point here is minus r and this point is r. So what is the first parameterization? For all x between minus r and r, because the x's are so if you have to stay inside that circle or on its boundary, x will have to vary between the leftmost point and the rightmost point. The leftmost point is minus r, there it is there, and the rightmost point is plus r, there it is there. And then simultaneously with that, y varies between the lower function, which is minus square root of r squared minus x squared, and the upper function, which is plus square root of r squared minus x squared. So this is the parameterization A, which is associated with this diagram. Now the parameterization B, which is I'll do now, and it is associated with this diagram, what we note is that for every y between this point, which is again minus r, because this is a circle of radius r, and this point here, which is r, so for every y between minus r and r, it is the function x that varies from the left hand to the right hand. Maybe I should have written, look out. So x varies maybe I should have drawn that in the first one as well. So for every y between these two, for example, if you take that value, which is between -1 and r, x will vary from the left semicircle to the right semicircle. So, and likewise here, for every x, for example this one, y will vary from the lower semicircle to the upper semicircle. Okay, so let me continue what I started writing here. So that is for every stupid machine. Okay, so for every x, for every y between -1 and r, x will vary between the left semicircle, which is r squared minus y squared, be less than x, and the right. Hold on a second.
I don't know what's going on.
I'll rewrite that again. So from x will vary from the left semicircle, r squared minus y squared, to the right one, r squared minus y squared, to the right semicircle. So that is from here to here.
Okay.
So that circle, in other words, this circle can be seen both as x simple or y simple. And again, this will be a defining example of what we'll do later on when we invert the order of integration in a double integral. Okay, now continuing further. Okay, continuing further, consider the simple region. So it is both x simple and y simple, which means that it is a rectangle. If you are to describe the x-coordinates within that rectangle, they vary between points A and B, and if you are to describe the y-coordinates, they vary between C and D. So, in other words, the boundaries are the straight lines with equations here. This one, if you walk on that line, y is everywhere equal to D. If you walk on this one, y is everywhere equal to C. Right, everywhere there. So if you are on this one, x is everywhere equal to A, and if you're on this one, x is everywhere equal to B. So the region inside we call R, and that region R, right, is described as follows. So you have an interval where x varies, so, and then we have an interval where y varies, so this is x belong to that interval, x varies there, and y varies there. So we say that this interval R, so we say that the region, and not interval, the region R is the Cartesian product of the intervals AB and CD, and we write R. It's not R as the real axis. The real axis is denoted by this, and this is not the same, so it's just R, that region here. R is AB cross C, D. Note that the order is of paramount importance. It is x that varies in the first interval, y that varies in the second interval. So this is a segment of the real axis, and this is another segment of the real axis, so we have two copies of the real axis. Okay, so what we'll do next is we'll choose a partition of both intervals a, b and c, d. So choose partitions of a, b and c, d.
Who the
as
fuck
follows.
joined?
The point A
Who the fuck
we're
joined
going to
this stream?
call x0.
Joseph.
Then we'll have point x1, which is bigger than x0. We'll have point x2.
Same.
Here somewhere we will have
Honestly, I just
xi minus 1.
nothing is going in anyway.
The next one will
But
be
I'm trying.
xi. The second last will be xn minus 1.
I'm gonna wait for you to reply in like
And the
5
last
years.
one, b, will be
Bye.
xn. So what we have, this partition is a,
And
which
then you
is
wait for me
x0,
to
which is
reply,
strictly
and then
less than x1, strictly
just take
less
forever.
than x2, so forth, less than xi minus 1, less than xi, less than blah blah blah, xn, which is equal to b. And in the exact same manner, we are going to do a partition of the
He left.
interval cd,
Oh.
where y0 will be the first point, then y1, then yi minus 1, less than yi, less than yn, and that would be equal to b. So we again take n points. But strictly speaking, you can take m, it doesn't matter, we'll send n and n both to infinity. So that's what we write here. You have y0, then here y1, somewhere here yi minus 1, the next one will be yi, and you go up until you hit point D, and that would be point yn. So basically on the graph I just did this. Let me do a partition, so I'll show you how that works with fewer points. So I'm taking n equal to 4, and so this is y, and let me draw the region. Like that. So we have A, which is x0, then we have B, which is x4, and then we have x1, 2, 3, that's supposed to be a straight line. Okay, so all lines here are straight. And then likewise, here we have C, D. So y0 will be C, y4 will be equal to D, and then I have y1, y2, y3. Okay, so these are the different cells, and let us mark this one. So this one here that I marked. So I'm going to call this R, J, K. Okay, I've used 4 partition points, but let us now think that they're more than them. So that's R, J, K. So what is R, J, K? R, J, K would be, change the, okay, so R, J, K. So this one here will be R0, 0. So it is the left hand that defines the the indices. So because x0, y0, so it is r0, 0. So rjk will have j, so that will be the xj here, and that will be yj. That would be xj plus 1. That will be, or maybe I should write here, this point has coordinates x, y, k, beg your pardon, xj, yk, xj plus 1 plus 1 yk. This point here will be xj plus 1 yk plus 1, and this point here will be xj yk plus 1. Right, so that's quite clear what that is. So therefore rjk is the Cartesian product of the following two intervals, xj plus 1 times yk plus 1. Right, okay. Now what I'm going to do is I'm going to plot that the function f. Now if I do it here, so this is our x-axis, this is our y-axis. Along the z-axis we plot some function f of x and y, and this function is defined over this simple region. So that would be point C, that would be point D, that would be point A, that would be point B, and in here somewhere in here is this guy. This small patch rjk. So the function, when you plot the function, it will give you a surface like that. Of course, depending on the function, there are very many functions. So I'll give you an example with such a function. There I use Wolfram alpha to plot the function sine x times cosine y. So that's a function of two variables. So this is the x-axis here, this is the y-axis, and along the z-axis it is the function. So it looks like this boxes for x, and so depending on the function, there are very many, I should say there's infinitely many functions that you can think of and plot them. So in our for our purposes, what I've drawn here in purple there on this one is the graph of the function. So what I'm going to do is I'm going to consider the following. So I'm going to single this one out, this small patch rjk. So this is it again. This is the patch rjk, and on top of that patch is the graph of the function, the surface of the function, which is obtained for the different values of x and y, which are entirely from this patch. Okay. Now what I'm going to do is I'm going to calculate the volume of that. So what is volume? Volume is height multiplied by area of the base. So this is the base. So this point here along the x-axis is xj. This point here is xj plus 1. This point here along the y-axis is yk, and this point here is yk plus 1. So the area of the base is a rectangle, is equal to xj plus 1 minus xj, which is this length from here to here. I should have changed the color. So this length from here to here. So you subtract the left hand from the right hand. So that's that, and then multiply it by this length, which is similarly yk plus 1 minus yk. Okay, so next I'm going to choose an arbitrary point, xi. So let me call that, or c, just probably don't like Greek letters, cjk. So cjk is an arbitrary point from that patch. And then I'm going to calculate the value of the function at that point. So that will be a point from the surface. And this height will be the function calculated at point cjk. Right, so this point cjk is characterized by two coordinates in the xy plane. The first coordinate is a number between xj and xj plus 1. The second coordinate is a number between yk and yk plus 1. So that cjk is the arbitrary point in the patch rjk. Now let us form the following: f cjk, and then we have xj, and that would be the height. I should say the height is f at cjk. So let us form the product xj plus 1 minus xj, and then yk plus 1 minus yk. So this is the area of the base multiplied by the height. Right, so that would be, let's go, let us call that delta vjk, and this will be the volume inside that. So delta vjk, I'll write it here on top, delta vjk is the volume of the the volume under the graph of f of xy over rjk, over that patch. And when we do double integrals, you should think at all times of ordinary integrals of a single variable. So recall, for a single variable we had to integral from a to b. We divided that into very many subintervals here, took one of them, then we took the arbitrary point on that one and calculated the area of this strip, and then we added the areas of all possible strips to get the area under the graph. Now what we do is we do a transition from 2 dimensions to 3 dimensions. So here we had a function of one variable which was plotted along the second axis. So you have one axis along which you plot the function of the values of the argument, and another axis on which you plot the functional values. Here we have two axes, x and y, over which you plot the values of
To wszystko, co tutaj też jest też? Znaczy szukierków. I to dużo zdradziłeś z tych wykładów?
Nie tak dużo.
Dobra, występ mi tylko tutaj A, nie wiem czy ty wiesz, ale to są twoje ciuchy, nie? Mam cię poprasowało. A zaraz znajdę.
Co?
Widmo.
Mhm.
No, pytałam się ciebie, tak mówię, a...
Tatuś ostatnio mi gadał, że ten...
To co?
że wypiliśmy mu całe wino z Francji.
Ja tam był przed...
Nie mam tego, nie?
Zaraz coś znajdę, ale tego chciałam iść, bo myślałam, że wezmę tam za 15 za 2 i wypijemy, ale ty powiedziałeś, że nie będziesz pił, to sama nie będę piła, bo to jest, no to poszłam się umyć.
Jest jeszcze białe wino, tam Maria też podobno. Można mix match, jakby co.
No ja
Możesz
już teraz
wziąć ją.
włosy mam mokre.
No to spoko, zostaw. Które godziny?
Chyba, że
Jeszcze...
do tatusia zadzwonię, żeby kupił po drodze.
Okej. Obojętnie. Możemy później jeść albo coś. Why is the camera latency so bad sometimes? Or is it me? Why is the... Oh no, yeah, it is. The latency is pretty bad, man. How do I make it better? I don't know, I don't... Shows on my OBS as well. It's kinda jumpy or whatever. I don't know. I don't fucking know.
The two variables of the function, and then along the third axis you plot the function of two variables. So the ideas get promoted one dimension up, so areas will clearly become volumes.
Clearly.
So that product here, in the exact same way as we formed the product for a function of a single variable, you've encountered that in earlier modules. I'll quickly remind you how that was done. So what we have was this. So you have x-axis, you have y-axis, and then from a to b we had a function f like that, and that interval is split into subintervals. So this is x0, this is xn, and then you have x1, x2, xi, the next one xi plus 1, and so forth. So let us take this interval here. So this is it, xi plus 1. So this is the function f between these two. So you take this interval here and zoom in, so this is what you get. Then you take the arbitrary point ci, so ci is an arbitrary point between the left hand
I don't fucking know why
and the right hand, with both ends allowed. And then you calculate the function, so this is ci, and then you calculate the function f at that point. So f ci, this is the height, and then multiply by the length of the base, which is xi plus 1 minus xi. So this is clearly the area. Well, not quite the area, because that will be the area of this rectangular strip. Now our function changes when you go from the left hand to the right hand. But if these 2 points are very close to each other, the function will not change much. So if these points are very close, you can safely assume that the function is practically constant between these 2 points, and that is that value here. So that would be the area. So let me call delta A, and let me put an index I, because this is the area of the ith strip. So think of that. I mean, just like cut it here with scissors, right, and then run a shredder to get a very fine shredder to get very narrow strips. So you can safely assume that each of these strips is actually a proper rectangle, and that would be the area, height multiplied by length of base. That would be the area of that rectangle. And then if you sum all such areas from 0 to n, right, and if you make sure that there is very many such strips, so many that they are infinitely narrow, so that this approximation of that irregularly shaped strip with a regularly shaped one with a rectangle is legitimate. So the sum over these will be the area under the graph. And that would be, now what is the area? Limits and approaches infinity. And then we have sum from 0 to n. Actually xn, so it's I plus 1, so it will be 0 to n minus 1, because the last one will be n of delta ai, and delta ai is f of ci delta xi, where I've written that as delta xi. Delta xi is xi plus 1 minus xi. Therefore, so that's what the area is, and we write this. This is the Riemann sum. This is called Riemann sum for f of x over the interval a b, and we write that sum. So where do I cut this out? We write simply
Definitely paying attention.
nah, let's
Even
find
though-
this. Sorry, I couldn't find it. Disappeared somewhere. So what we had, let me remind you, we have the area under the graph of f of x for x between a and b is equal to limits and approaching infinity sum I runs from 0 to n minus 1 delta ai, so that is the area of the height strip, which is limits and approaching infinity. I runs from 0 to n minus 1 f of ci, so ci is the arbitrary point between xi and xi plus 1 times delta xi, where delta xi is the right hand minus the left hand, and this is what we write symbolically as integral f of x, so that is f, and delta becomes d, and we write a to b, and we say that this is the definite integral of f of x for x from a to b. Okay, so this is what we had for a function of one variable. Now for a function of two variables, the generalization is absolutely straightforward. So we had that patch rjk, and that, fortunately, these are no longer available, so that is the lid on top of it. So this is the function. So we take the arbitrary point, so that is this point here is cjk, this is xj plus 1 as yk plus 1. So again rjk is xj xj plus 1, the Cartesian product of this interval with yk plus 1. Cjk is a point from rjk, any point there. So we form the volume. Now before we had here area, of the ith strip. Now this will be the volume of the, what do we call it, jk slice, and this will be the value of the function at this point, which is the height. So you see the analogy between an integral of a single variable is, with an integral of a single variable, is complete. So f of cjk, that is nothing else but the height, and that has to be multiplied by the area of the base. So this is the base. The area of the base is equal to delta, so I should say first xj plus 1 minus xj multiplied by yk plus 1 minus yk. Let us, for brevity, denote this by delta xj, and for brevity denote this by delta yk. So, and this is the volume jk, because this is the volume of that slice. So, I mean, out of all possible slices, basically what we do is we have this three-dimensional drawing like this. So this is the lid there, right, like that, and our slice is here. So we consider the volume of this pillar which is inside. So basically what we do is we chop, not like a shredder in this case, when you have a function of a single variable. So you cut along the graph of the function and then you shred it like that. Now if you look from above the z-axis, you shred it with a knife, which is like that. So we get like these columns, and this is, I should say, slice or column. So we get volumes now. We don't get areas as before, we now get volumes. Okay, so what we'll do is then the volume under the graph of the function. Now this is the important thing. The volume, and compare at all times to this the volume under the graph of not f of x, it is f of x and y, for x between a and b and y between c and d, so that is the entire volume, is the sum of these volumes of the individual slices or columns, just like here, the sum of them, but they have to be very many so that we can justify taking the roof here, or the roof of each column as a flat one. So in complete analogy to this, so I write that the volume is, I'll continue, so the volume under the graph of the function is, let's see if I can move this one somehow. Sometimes it does, but not all the time it moves. Okay, so what is that volume is, and I'll continue on. So keep in mind this, I'm going to replicate that when I introduce the double integral. So here, that's how I introduce the single integrals, integral of a function of a single variable. I'm going to write that for the function of two variables, f of x, y, which is here, f of x and y. So that volume under the graph of f of x and y for for x between a and b inclusive and y between c and d inclusive is equal to limits and approaching infinity. We have then the volume, which is the volume from the previous one. Now we have VJK, so we have to do that for each of the slices. So we're going to sum for all slices along the x-axis, and then we have to sum for all slices along the y-axis, so there will be a double sum. Sorry, there will be a double sum.
Oh, I fucking saw it.
Okay, that completely. So, new one. So there will be a double sum. So the volume is equal to sum. Sorry, beg your pardon. Limits and approaching infinity. Sum j
You want
runs from 0 to n minus 1. K runs from 0 to n minus 1. Delta vjk. So this is the volume. So this here only is the volume of the jkth column or pillar or slice. So you sum or all slices along the y-axis and then you sum along the x-axis. So it's a double sum, and then you make sure that these numbers tend to infinity. The numbers, you know, the number of cuts along the x and y-axis respectively are infinitely many. So what is then that? This is limits and approaching infinity. Then we have, let me write the, okay, I'll write them as two separate sums. N minus 1 sum from 0 to n minus 1. What is delta vjk? This is f of cjk, and we said delta xj times delta yk. And this here is called Riemann, just in complete analogy, a Riemann sum, in complete analogy to the case of a function of a single argument. Riemann sum for the function fxy over the region R, which is AB cross CB, and is written as, symbolically, integral over R, so it's a double integral f of x and y dx dy. So that is the meaning. So clearly a double integral of some function f over some interval, a region R in the xy plane, is nothing again but the volume of the figure which has R as base and f of x and y as roof, or roof, yeah, that's a good way to say it's a roof. So that's what a double integral of a function is. So this here, f of x dx from a to b, is the area under the graph. So clearly this is the volume. So under the graph here of f of x, and this is the volume under the graph of f of x and y. So when you have a function of one argument, you can only talk about areas. When you have a function of two arguments, you go one dimension up to plot it, and then you talk about volumes. So this is the in the limit, in that limit, when n approaches infinity, that only then we write this sum of these individual volumes as that integral. Okay, so that is the integral of a function of two variables, and this is what it represents. This is the volume under the graph of the function. Next thing is I will do in the next lecture. I will show you how we can calculate double integrals as two integrals of a function of a single variable, and we will exploit the so-called Cavalieri's principle. So this is the end of the.
I will let you
In
finish.
the next segment, we'll consider Cavalieri's principle, or the so-called slice method. Suppose we are given a solid, some solid, and think of that solid as,
Solid shit.
let's think of a cucumber. So this is the solid S.
He's definitely a Slav. He is definitely a Slav.
And suppose we want to measure
When
the
he
volume
thinks of a solid,
of
he
that
thinks of a
cucumber.
cucumber.
So this is what it looks like.
Okay, I gotta tell the boys. Yo, I just wanna say, Emil, when he thinks of a solid thing, he thinks of a fucking cucumber.
Oh yeah, Thalia.
I fucking died.
A nice
I
big
was like,
fat cucumber up his
he's definitely a
brain.
Slav. I was like, he's definitely a fucking Slav. When he thinks of a solid, he thinks of a fucking cucumber. I'm dead.
Not as dead as when he's about to say A0 and then his fucking Siri wakes up. So you're like what, week 8, I'm guessing?
7. End of 7.
End of 7, so you're week 8. I was fucking spot on.
Yeah.
Trying to figure out.
I can't hear you, you broke out there. Better.
I'm trying to do calm, and I'm finally starting to get depression.
Yeah. Good.
Yes.
Without depression, there's no. Yeah.
Without
Okay.
depression, you can't be unpressed.
Bye.
Bye. Have fun with fucking Emil's big fat cucumber.
Yeah.
So this is a three-dimensional picture. Okay, so what we are going to do is we're going to introduce a coordinate system in such manner that the x-axis of that coordinate system goes through that solid, so that's like that. So this point here, the leftmost point, is say A, and the rightmost is where the x-axis pierces again out. That point is a B, so we also have y-axis there, and we have the z-axis here. Okay, so what are we going to do now is we are going to cut or slice. So think of these scissors that have many blades, you know, for slicing salads, and this is exactly the type of thing we do. So we slice with planes which are perpendicular to the x-axis, like that. So these are the different slices. Each of these slicing planes is again perpendicular to the x-axis. And let us consider one such slice. Okay, so that particular slice, which is between these two planes, so this part of the solid. So from there to there. Okay, so let us say that these points are these planes are the very first one at A, so it will be P0. So this is the leftmost plane, P0. The rightmost plane will be P0, or this is PA,
PN.
where A is. This is PN, and PN is where B is. So that's the hadron. So what we have here is again a slice. So let's say here, this point here is X. Okay, so A, or just as before. So along the x-axis you have A, which is x0. Then you have B, which is xn, as before. And we have the various partition points. So this is xi, this is xi plus 1. So this point here, let me use a different color. This is point xi from the x-axis, and this point where that plane is, so this is pi, this is pi plus 1, right? This is point xi plus 1. Okay. So what we get is, if I just select that, so think about it, you take a cucumber and you slice it, and you take one of these slices, so this is it, so this is one end, this is the other end, this is the slice between these two planes, so that plane is here, that plane is there. So they are the two planes. Let me, so this is the plane pi plus 1, cutting plane. This is the cutting plane pi, and that is the slice. So what is then the volume of that slab? Okay, so let us that slab that we form, so that slice of the cucumber, let us take a point, so along the, so the cucumber is between A and B. This is the left end of this, so this is xi, and this is the right end of this slab, so this is that point here, that is xi plus 1. Okay, so what is then the volume of this slab? The volume will be the height and what is the height? This is the height, so the origin is here somewhere. This point is xi, this point is xi plus 1 along the x-axis, so the height is delta xi, which is the right hand, xi plus 1 minus the left hand. So this distance from here to here is that distance from there to there minus the distance from here to here, clearly. So this is the height, so will be the height delta xi multiplied by the area of the cross section, area of the cross section. Let us call that area A of x. Now, if you go along the x-axis from one end to the other end, the cross-sectional area will vary, of course. But if the slices are very, very fine, very thin, then you can safely assume that the cross-sectional area does not vary too much. So again, as with an integral of a single variable, we choose a point ci, and that point will be any point between the left hand and the right hand. Right, so that's why I'm writing on top here. So this point ci will be an arbitrary point from within. Let me use a different color for it. So this is the point ci. So ci is a point from between from the interval between xi and xi plus 1. And then if the slice is very, very thin, just as we introduced the concept of an integral of a single variable, so what we do is the cross-sectional area at that arbitrary point multiplied by the height xi plus 1 minus xi, which is the same as the area of the cross-section at point ci multiplied by delta xi. So what would that be? That would be the volume of this slab that is between these two planes pi and pi plus 1. So because this is a volume, let us call that volume v delta vi. Okay, so the volume delta VI, again, delta VI, the volume of this slab that is between these two planes, so that here, this volume here is equal to ACI, that is the area of the cross section at the arbitrary point along the x-axis between the two ends, multiplied by the height, delta xi. Okay, so what I'm going to do now is I'm going to say that the volume of the entire cucumber is equal to the sum of the individual slabs or the individual slices that you obtained after slicing the cucumber with planes perpendicular to the x-axis. So if there are infinitely many of these, so the volume V will be equal to the sum I runs from 0 to n minus 1, from one end to the other end of delta Vi, and if there is sufficiently many, how many? Well, infinitely many, that many. So if there are very many of them, then this is exactly the volume of the cucumber. So this is then equal to limes. Now let us recall what delta Vi is. N minus 1. That will be A of Ci delta Xi, and this is nothing else but the Riemann sum for the function A of x, the area of the cross section, for x in the interval from A to B, and this volume is then integral from A to B, A of x dx. So this is the Cavalieri's principle. So this is how we calculate the volume of a solid, the cross-sectional area of which changes when you go from one end of the solid, positioned at x equal to A, to the other end of the solid, positioned at x equal to B. So what you have to do is integrate the cross-sectional area from one end to the other. This is Cavalieri's principle. And this is what we will use in order to calculate a double integral. So the idea behind that is in the following. So let me draw so this is the it has to be right angle. Okay, so this is the z-axis, this is the x-axis, this would be, okay, it goes into the y-axis, a right-handed coordinate system. That's what I'm trying to plot here. This is the z-axis. Okay, and then we have our region R, which is x is between A and B, y, this is the y-axis, y is between C and D. Okay, so this is the region R, and then we plot the roof, which is the function f of two variables x and y. And this is the graph of this function. So this is the roof is f of x and y. For the different values of x and y from within the region R, they're different functional values, and when you do that for every single point from R, you get the roof of that. That is the graph of the function. So what we'll do first is we cut with planes first. We cut with planes perpendicular to the x-axis, just applying the Cavalieri's principle. So apply the Cavalieri principle in two manners. Firstly, cut with planes perpendicular to the x-axis. So let us do that. Okay, so that is one such cut. So this here, here's a different color. This is the curve from the surface f of xy obtained when you cross that surface with the plane here at point xi. So here x is equal to xi. Likewise, cut with another plane. So we cut with very many planes actually, like that, and that would be the surface. Cut with that plane will give you another curve like that. So what we need is to calculate the volume. So here this plane is at xi, this plane is at xi plus 1. So what we need to calculate is the volume under the graph. So if you drop perpendiculars like that, so you see this shape here.
I wonder if it just... it doesn't...
Okay, in the next segment, let us now find the volume of this purple slab that we obtained when we cut with planes perpendicular to the x-axis, and so that's the Cavalieri's principle applied first by cutting with planes perpendicular to the x-axis. So this particular slab here, this looks like that when we zoom in. Okay, so these are the different tops. So that is a straight line, that is also a straight line, that is a straight line, and we have the just single out the axis. These are the straight lines here. Okay, so this x-axis is there. So here we have xi, here we have xi plus 1. Now, the idea of Cavalieric principle is to take the cross-sectional area and integrate it. So what we need is the area of the cross-section. So let me take the point here Ci, which is between, again, xi and xi plus 1, and then the plane, the cutting plane at Ci will yield this. Okay. So what we need is that area here. What is that area? Now take this sheet and look at it from the perspective of the x-axis. Look where the y-axis is. The y-axis is here, and the z-axis is above. Now let us rotate and have a look from the viewpoint of the x-axis. So we look from here. So at the yellow one will look something like that. Maybe I should use yellow bullet. Okay, so where are these 2 points? Here we have y is equal to c at descent, and at descent, so the y-axis goes further there, y, descent y is equal to d. So here we have the z-axis, which is going up. Sorry, the z-axis, which is up, the z-axis that is pointing towards you, and then we have the y-axis, which is in this direction, and this here is d, and this here is c. Okay, so what we are asking is, what is the cross section? So here we have ci, that's important. So this is at x equal to ci. So here our function, this is the graph of the function, this is the top here. X anywhere on that yellow slice is fixed at ci. So this is f, x is fixed at ci, and y varies between c and d. Now what we need is that area. Now what is that area? It is integral of that function from one end to the other, from the smaller to the bigger. So let me cut
Myself.
right there. Get rid of that. Go without infections this time. There. Okay. Now continue writing with yellow. So the area of the cross section and that is the cross section here, the yellow one, the area of the cross section, which is at x equal to ci, right? That is x is equal to ci here in that function, is integral from the smaller to the bigger the function ci y dy. So the cross-sectional area is a function of y, and let me call that function a of y. Now what we'll do is, in order to calculate the area of the cross-section, right, so what we do is calculate f at cy dy. Now what is then the volume? The volume, that is Cavaleri's principle, it is the cross-section integrated from one end to the other, from a to b. So the volume is equal to integral from a to b over x, right? Integral. Now this is integral from c to d f of ci y dy. Now that ci is a number between xi and xi plus 1. So for that reason, because these are very thin, I'm simply going to write x here, and this is what the volume will be. Integral from a to b, then integral from dx, integral from c to d f of xy dy dx. So this is called an iterated integral. So the double integral, which is the volume under the graph, which is integral over r f of xy dx dy, we write this, which is nothing else but the volume, we write this as an integral first over y and then integral over x. So let me write this on a fresh page, and we have the following. So integral over double integral over the region r f of xy dx dy is equal to integral from a to b over x of integral from c to d f of xy dy. So this is called, see here, iterated integral. So when you have a simple region, you slice with planes perpendicular to the x-axis, calculate the area at each slice for every x between A and B, so I had Ci. Okay, now because that will vary from one end to the other, we'll simply rewrite x instead, and we have this. This of course can be written as, without writing the brackets, they're not needed. So look, that is now clear what happens. Fx y dy. So here, this is a definite integral from c to d, and the variable is y. So when you integrate over y, this remains a function of x. So that means that depending on where that particular slice is, the cross-section area will be different. And that function of x, when you integrate it from a to b, gives you a number, and that number is the volume under the graph of f of x, y. Similarly, if we cut with planes perpendicular to the y-axis, not the x-axis, perpendicular to the y-axis, we obtain integral of r f of x y dx dy is integral from c to d, integral from a to b. Now we first integrate over x, so this would be a function of y, and then we integrate that function with respect to y. So if you can write this as integral from c to d dy, integral from a to b f of x comma y, and we integrate over x. So again, integrating over x yields a function of y, and when you integrate this function of y with respect to y, it gives you a number, and that number is again the volume under the graph of f of x and y. And because the volumes are the same, therefore, and that these are the same, therefore what we have is the equality of this and this. So these two are equal, or if you prefer, these two are equal. I mean, it's just a different way of writing the same thing. Okay. So these two are equal, and these two are also equal, and they're equal to that integral of f over the region R, integral of the function of two variables f over the region R, which is nothing else but the volume under the graph of the function. So this is how we represent double integrals with iterated integrals. And the next thing I'd like to do with you is solve examples. So let me try examples. So consider the function f of x and y, which is 1 minus x. Well, clearly that function is not actually a function of two variables. It is a function of one variable, only x, but it is embedded, it's promoted in 3 dimensions, and the region of interest is the Cartesian product of the interval 0, 1, 0, 1. Okay, so what I'm going to do is I'm going to plot the function. Actually, I have it plotted here in Wolfram Alpha. So you see here, I have to say plot. If I say plot 1 minus x, it will give me a straight line. Let me show you that. If you just say plot 1 minus x, like that, it will just give me the straight line 1 minus x in the 2-dimensional plane xy. So to trick Wolfram Alpha into thinking that that is actually a function of two variables, I have to say plot the function of two variables, 1 minus x. And now the straight line will become a plane, and that is, there you go, it understands it correctly. So this is that plane here. That is that plane. So what we want is to say that x and y, I should say x, maybe if I try putting brackets around that, right, plot, and then say that x is from 0 to 1, and comma y equals 0 to 1. Okay, so that is our region. There it is. So what we want to do, this is the graph of the function. So you see the region of integration will be from 0 to 1 along the x-axis there, and then along the y-axis, which is here on top, denoted on top, I mean this is also the same thing, it is from 0 to 1. Okay, so that's that, and that is the function z, which is given along the vertical. Okay, now what we need is this function. So what we have to calculate is the volume and the graph of the function. So we need the volume of this wedge, you know, to calculate the volume of the wedge. Well, it is quite clear what it is, but let's use double intervals to calculate that. So what we need is the following. So example number 1, the volume is integral over r. R is that guy here, from 0 to 1, the Cartesian product of the intervals from 0 to 1 with the interval from 0 to 1, f dx dy, which is integral over r. The function is 1 minus x dx dy. So what we're going to do is we are going to cut with planes which are perpendicular to the y-axis, and then so that how it will look like. So this is x-axis, this is the y-axis, this is the z-axis. Okay, so this is point 0, this is point 1, this is also point 1, like that. So we now cut with planes like this. So there is plane, that is the cut there. So we have a triangle that is formed, and we want to calculate that area and then propagate from one end until the other one. So basically what we then have is that this is equal to integral. X will vary between 0 and 1, and then we have integral from 0 to 1, 1 minus, y will vary between 0 and 1, because there will be the different planes, 1 minus x dx. Okay, so this is the iterated integral, and what we then have is this bit here is integral of dx is x in limits 0 to 1 minus x squared over 2 in limits 0 to 1, which is 1 minus 0 minus 1 squared over 2 minus 0 squared over 2. So this is 1 minus a quarter, and that would be 1 minus half, and that will be 1 half. So this integral is 1 half, so therefore this is equal to integral from 0 to 1 half of dy, which is 1 half integral from 0 to 1 dy. So what's that integral? This is y in limits from 0 to 1, or simply 1, so the whole lot is equal to 1 half. So that is that area, it is 1 half. And you can get the exact same if you cut with planes perpendicular to the other axis. Therefore then this volume will be equal to integral from 0 to 1, right? dx integral from 0 to 1, 1 minus x as the function times dy. Now when you integrate over y, this is a function of x, so this is a constant when it comes to integration over y, so you can take that one outside there. So you have integral from 0 to 1 dx times 1 minus x times integral from 0 to 1 of dy. This integral is y in limits from 0 to 1, which is 1 minus 0, and that's equal to 1. So the whole lot becomes integral from 0 to 1, 1 minus x dx, which is times 1, of course, that one here is times 1. So this is what? This is integral of dx from 0 to 1 minus integral x dx from 0 to 1. The first one is x and limit 0 to 1. The second one is x squared over 2 from 0 to 1, the same as here. So this 1 minus 0 minus 1 half 1 squared minus 0 squared over 2. Excuse me. So this is equal to a half as before. So it doesn't matter how you're going to, either you're cutting with planes perpendicular to this axis, or you're cutting with planes perpendicular to the x-axis. So when you do that, you get that is the picture here. That is that area, and then you propagate this rectangle, because it will be a rectangle. You propagate it from one end, from 0, that is the biggest one, down to that one, and you y will vary between 0 and 1, because there will be the different planes. 1 minus x dx. Okay, so this is the iterated integral, and what we then have is this bit here is integral of dx is x in limits 0 to 1 minus x squared over 2 in limits 0 to 1, which is 1 minus 0 minus 1 squared over 2 minus 0 squared over 2. So this is 1 minus a quarter, and that would be 1 minus a half, and that will be 1 half. So this integral is 1 half. Because it will be a rectangle. You propagate it from one end, from 0, that is the biggest one, down to that one, and you get absolutely the same area. Okay, in the next example, we consider example 2. Z, along the z-axis we plot the function x squared plus y squared. This is a paraboloid. The interval is the Cartesian product of minus 1, 1 with 0, 1. So let me plot that one. So instead of this, I'm going to plot now x squared plus y squared, and then the interval is along the x-axis from minus 1 to 1, and the other one is from 0 to 1. There it is. Okay, it is. Maybe I should make it bigger so that you can see. Let's get minus 5 to 5, from 0 to 5. Just extending it. Wow, it doesn't. Okay, so it's like a cup. I mean, it doesn't plot it well, so I'll try to plot it better. So what we have in the xy plane, in the xy plane, we have z is x squared plus y squared. So what is x squared plus y squared? I mean, these are circles. So
These are circles.
forget the z-axis like this. So that'll be the y-axis. That will be the x-axis here. And then we have a cup like this.
No,
So hope you get
u mnie jest wszystko.
okay. So if you slice that cup with a plane which is perpendicular to the y-axis, so let me get this plane. So this is the plane of the cut. Then what you'll get in result is a parabola. Because if you slice at a certain value of y, say y is 0, so you fix y is 0, also what you get is a parabola. So z, which is y is 0 squared plus x squared, this bit here, this is a parabola. So this is your z-axis, this is your x-axis. When x is 0, that is y0 squared, so this number is y0 squared, and this is the parabola. Like that. So it is a parabola. So basically every slice with a plane gives you a parabola. So if you cut with a plane at y equal to 0, then you get a parabola going through the origin, and then you get a parabola like that, and so forth. So I hope you get the picture. Okay, so what is then the volume of this cup? So what we're saying is that x varies between -1 and 1. So let me extend x a little bit. So x varies between -1 and 1. So from there to there. And y varies between 0 and 1. So between there. So it's kind of half of the cup. Okay, so half of the cup. If you put -1 there, that will be the other half of the cup. So, okay, and the volume is integral, double integral, over the region R, f of x and y, dx dy, which is integral over R. The function is x squared plus y squared dx dy. beg your pardon, x is between minus 1 and 1, and then you have x squared plus y squared dx. Okay, right. Okay, so these are planes from x or the volume is equal to, now planes are perpendicular to the y-axis, and that is from 0 to 1, x squared plus y squared dy, and then you integrate over x from minus 1 to 1. And both will produce the same result, depending on how you slice. Whether you slice with axis planes perpendicular to the x-axis, this, right? Then these planes are between minus 1 and 1. So that is the picture here with the yellow ones. Whether you slice with planes perpendicular to the x-axis, and these planes are, you know, for between y equal to 0 and okay, so let me calculate both integrals. So let's call this a, let's call this b, and we will see, you will see that we get absolutely the same result, and this is of course the volume. So a, this is integral from 0 to 1 dy, integral from minus 1 to 1, and then we have x squared plus y squared dx, which is integral from 0 to 1 dy. I don't touch this part, so this is what I'm handling now. Now integral of x squared is x cubed over 3, the limits are from minus 1 to 1, plus y squared, y is a constant, so there will be y squared integral from minus 1 to 1 of dx. So this is what? This is integral from 0 to 1 dy. Then we have 1 cubed over 3 minus 1 cubed over 3. That is this part. And then we have plus y squared x from minus 1 to 1. Now this is equal to 2. But it is 1 minus minus 1, 2. This is equal to 2/3. So we get that this is integral from 0 to 1 of 2/3 plus 2y squared dy, which is 2/3 integral from 0 to 1 of dy plus 2 integral y squared dy from 0 to 1. The first integral is 1. The second one is y cubed over 3. Y cubed over 3 gives you y cubed over 3 in limits from 0 to 1. This is 1 cubed over 3 times 2, so it is another 2/3. So the volume of that half cup is 4/3. Okay, now let us find the volume with the other repeated integral b, iterated integral or repeated integral. So what we'll do next is integrate, so b, so that's that bit, so the volume will simply be integral from minus 1 to 1 dx, integral from 0 to 1 x squared plus y squared dy, which is integral from minus 1 to 1 dx, and then we have x is a constant when you integrate with respect to y. I can take it outside brackets, and then outside of the integral, and then you have integral from 0 to 1 of dy plus integral y squared dy from 0 to 1. So this is integral from minus 1 to 1 dx of the following: x squared, now integral of dy is y in limits 0 to 1, plus y cubed over 3 in limits 0 to 1. So this is equal to integral from -1 to 1 dx, x squared, this is equal to 1 minus 0, which is 1, is equal to 1 cubed over 3 minus 0 cubed over 3, which is 1/3, so it is 1 minus 1/3, like that. So the whole lot becomes now this integral of a difference, so this is difference in integral from -1 to 1, x squared dx, minus 1/3, integral from -1 to 1 dx. The first one is x cubed over 3 in limits from -1 to 1. The second one, integral of dx, is x in limits from -1 to 1. So this is equal to 1 cubed over 3 minus 1 cubed over 3 minus 1/3, 1 minus 1. Okay, so this is what? Sorry, before I say, I notice that this is 1/3 here, and for reasons so now I made it minus, so it's a plus here, right? So this is the plus sign coming from there, so it's a plus, beg your pardon, plus, alright, and that's how it will give us 1/3, plus 1/3 is 2/3, and from here plus 1 plus 1 is 2, plus 2/3, so the whole lot is 4/3. So that shows you that it doesn't matter which way you're going to slice, the volume of the cup is the same, so whichever way you look at it, and it will give you the same answer. Okay, so this is the second problem. Consider next the following. Consider the y simple region. So namely, let me quickly remind you, this is x, this is y, x is between a and b, then we have a function phi 2 of x, the function phi 1 of x. So phi 2 of x is never smaller than phi 1 of x, otherwise you have to split into separate segments. Okay, so for all x between a and b, so for example if you take this value here, which is between a and b, right, well, y will vary between the lower function and the upper function. So that is the way we write this, is B is the region A less than or equal to x less than or equal to B. Then we have phi 1 of x less than or equal to A less than or equal to B. Beg your pardon, to phi 2 of x. Phi 2 of x. Then integral over this y simple region D of f of x y dx dy is integral. So what you do is you vary x between phi 1, vary y, beg your pardon, between phi 1 and phi 2. Then you get f of x y dy, so y varies between that one and that one, so that's the cross-sectional area, and then you get a b dx. Or you can write this as integral from a to b, integral phi 1 to phi 2 f of x y dy dx. And very often the brackets are not written, So the first variable that you integrate over is the one that is written first. So that is the first integral is an integral over y, and then you integrate over x. I've put here the brackets like that so it's clear. You integrate over y first. This is a function of x, and then you integrate this function of x over x from a to b, and then you get the volume. Right? Now that can also be written like that without any bracket. It's clear. This is the integral that you do first. So this is a function of x because you integrate over y from one end to the other, from the lower curve to the upper curve, and then you integrate that. But in books, in standard notation is not to write it in a user-friendly way, but just to write it in this way. So know that it is y that you have to integrate first over, and then you integrate over x. So this one goes first, this one comes second. So that's what we write dy dx. In the exact same manner, if we get the x simple region, so similarly, if M is x simple region, okay, in this segment, in the next segment, similarly, if M is an x, okay, in the next segment, let us now find the volume of this purple slab. Okay, in the next segment, we continue with okay, in the next segment, let us now find the volume of this purple slab that we obtained when we cut with planes perpendicular to the x-axis, and okay, in the next segment, similarly, if M is an x simple region, namely y varies between C and D, and we have two functions of y. Say psi1 of y and psi2 of y, which is greater than or equal to psi1 of y, and this region here is our region M. Okay, so this is the next simple region. The way we write this is as follows. M is the region which, for every y between C and D, x varies between this function. So for example, if I take this one here, make that bigger, x will vary between these two functions for every y between C and D. So for every y between C and D, x will vary from the left hand, which is psi1, this function here, to the right hand, which is the other function, which is psi2 of x. And then, okay, in this segment, okay, M of x. And then the integral over M, which is the volume, of course, the volume, this integral over M of the function f(x) dx dy can be written as integral from c to d dy integral from psi1 of y to psi2 of y f of x y dx. So again, this is a function of, when you integrate over x, this is a function of y, and then you integrate that function of y with respect to y, and you get a number which is the volume under the graph. And that is, of course, integral from c to d of integral c1 y to c2 of y f of x y dx, and then you integrate over y. And as I said, people don't usually write the brackets, and it is clear from the context what's what. So it's f of x y. You integrate first with respect to x, and then you integrate with respect to y. So these are the same ways, you know, that is the same as that, the same as that, and that, and that, which is the volume. Now, let me give you two simple examples of how that works. So consider the following two problems. So the first problem, so two examples. I, which is the volume, so the function is x cubed y plus cosine x. The region is T, with T, the triangle, consisting of all points x, y, such that for every x between 0 and pi over 2, y varies between 0 and x. So let me plot it. So this is x, this is y, then x is between 0 and pi over 2. So so what is the graph of y is equal to x? This is it. This is a straight line, like that. So pi over 2. And then that would be also pi over 2 here. So y is equal to x. So for every x between 0 and pi over 2, so x varies between these 2 points. Then, for instance, if x is there, then y varies between the current value of x, whatever that is, and between 0, which is there, and the current value of x, whatever it is. So that x is a number between 0 and pi over 2. So that is the parameterization of the region of integration. The region of integration is T. Okay, so what we need is I is, now for every x, we said for every x between 0 and pi over 2, y varies between 0 and x, and the function that is given is this one, dy. So we have to integrate this function, so this is straightforward. So what we have is x is a constant when you integrate with respect to y, so what we have is x cubed y, integral of y dy is y squared over 2 in limits from 0 to x, minus maybe cosine of x times y in limits from 0 to x, and you close the bracket. So that is equal to integral from 0 to pi over 2. Then you plug in the limit 0, so this here is equal to x cubed multiplied by x squared over 2 minus 0 squared over 2. So this is x to the power of 5 over 2. So it is dx, then x to the power of 5 over 2 minus, now this bit here, y in limits from 0 to x is x minus 0, or simply x, so minus x cosine of x. Okay, so this integral is 0 to pi over 2, 1/2 x to the power of 5 dx minus integral from 0 to pi over 2 x cosine x dx. So this is equal to 1/2 x to the power of 6 over 6 in limit 0 to pi over 2. And then we have then I have to integrate by parts, so this will be x sine of x, x plus x sine of x in limits 0 to pi over 2 minus integral sine of x dx, which is minus cosine of x in limit 0 to pi over 2. So the whole lot will be that will be pi over pi to the power of 6, and you have 2 to the power of 6 times 2, that's 768 if I'm not mistaken. From here you have plus pi over 2, and from there you have minus 1. That is full stop. So that is that one. And consider another one, another example, example number 2. 2 is the following. Find the volume of the tetrahedron bounded by planes y equals 0, z equals 0, x equals 0, y minus x plus z is equal to 1. So there is a fancy way of writing this. So from here, z is 1 plus x minus y. If you bring these on the other side, this is what you get. So that is the function. And so x is 0, y is 0, so you have to plot it. Let me use Wolfram Alpha to plot it, just to show you how it looks like. So this is it, z is 1 plus x minus y, I have plotted it. And so what we have is the z equal to 0 plane, which is the floor here. Then the x equal to 0 plane, which is this side, and y equal to 0 plane, that is that side. So we have a tetrahedron, which I believe I can actually plot better than that. Let me do that. Okay, here it is. So now look, that is the function that we have to plot. It's best if you look at it at the different coordinate planes. So at the y equals 0 plane, that is zx plane. So this is it here. This is the x-axis. This is the z-axis. This here is the zx plane. So y is equal to 0. So when y is equal to 0, we have z is equal to 1 plus x. So the graph of the function 1 plus x, right? So this is when x is 0, so that is the origin here. When x is 0, z is 1. When x is minus 1, z is 0. So that is this part. Let me make that thicker. This straight line here has equation z is equal to 1 plus x. So this is our function. Z is 1 plus x minus 1, so it's a function of two variables. And when we are in the y equal to 0 plane, that plane here, then we have 1 plus x. Then at x equal to 0 plane, that is x equal to 0, this is the zy plane. So this is the zy plane here, right? So what we have in the zy plane is z is equal to 1 minus y, because x here is 0. If x is 0, so 1 minus y survives. So when y is 0, z is 1, so this is this point. Let me use this one. So this is this one, and when y is 1, z is 0, so we get this like that. So this here, the blue one, is z is 1 minus y. And finally, at the z equals 0 plane, what we have is 0 equals 1 plus x minus y. Therefore, y is equal to 1 plus x. Right, and there it is. This is the straight line 1 plus x. Because when x is 0, y is 1. X is 0 here, y is 1. When x is minus 1, y is 0. So this one is y is equal to 1 plus x. And the tetrahedron in question is now the solid, that is, so these are the sides of it. That one, then we have this one, right? Then we have the bottom which would be, say, that one. And then that's it. So let's find the volume of this guy. Okay, the volume of that tetrahedron. So what is right? Look at the base. The base is, let me now. Oh my God, oh, Father. Okay. So this here is the base of the tetrahedron. That. So what can you say about the base of the tetrahedron? The base, call the base D, so this is the in the xy plane, the base is the following. So for every x between minus 1 and 0, so x runs from there to there. For every x, for instance, for this value of x, y runs from there to there. So what is that one? 1 plus x. So for every x between, beg your pardon, for every x between minus 1 and 0, so there it is, there is x is between minus 1 and 0, so you select one of these, and then y varies between 0 here and this function, which is 1 plus x. 0 less than or equal to y less than or equal to x. And then what is the lit? What is the function? So I mean, how? So y is from 0 to 1 plus x, beg your pardon. And this is obtained by taking z equal to 0, because the base is in the z equal to 0 plane. There it is, in the z equal to 0 plane. By taking z equal to 0 in the function z is 1 plus x minus y. I mean, I had it here anyway. I mean, I did it once already. Okay, so this is it. And then the function that the height z for every now point in the region D, the function z is given by this. So I will continue on the next page. So the volume is equal to z of x and y dx dy over this, how did we call it? We called it D, the region D. which is in the z equals 0 plane. So d, again, is for every x between -1 and 0, y runs between 0 and 1 plus x. And the function, so this is the region D, the function z is equal to 1 minus y plus x. So therefore our volume is integral from region over the region D, 1 minus y plus x dx dy, and this is the integral. Now x is between -1 and 0, and for every x between -1 and 0, y runs between 0 and 1 plus x. The function is 1 minus y plus x, and you integrate that with respect to y. So this is integral from -1 to 0 of the x integral. Now let's split that three integrals here of integral from 0 to 1 plus x of dy minus integral y dy from 0 to 1 plus x plus integral. X is a constant when it comes to integration with respect to y, and 1 plus x of dy. So this is equal to integral from -1 to 0 dx. Then integral of dy is y limits 0 to 1 plus x minus integral of this is, beg your pardon, this is dy here. Integral of y dy is y squared over 2 in limits 0, 1 plus x minus x. Integral of dy is y in limit 0, 1 plus x. So this integral from -1 to 0 over dx, then 1 plus x minus 0, that's the first one, minus 1 plus x squared over 2 minus 0 squared over 2, that's the second one, minus x. Then what we have is 1 plus x minus 0, and you close this. So that would be integral from -1 to 0. We have is dx here, and then 1 plus x minus 1/2 of 1 plus x squared minus x 1 plus x, like that. So I can take 1 plus x outside bracket, so it's from -1 to 0 dx, and then 1 plus x outside brackets, and inside the brackets from here we have 1, from here we have minus 1/2 1 plus x, and from here we have minus x. So this integral from -1 to 0 dx, 1 plus x, and then 1 minus 1/2 is 1/2, and then we have -1/2 of x minus x is -3/2 of x. Okay, so I'll continue just by cutting here, make it cleaner. But let's get rid of this. So I'm continuing on top. So this continues on top. So this is equal to integral from -1 to 0 dx, and let's open up the bracket. So we have 1/2 minus 3/2 x plus 1/2 x minus 3/2 x squared, right? So 1/2 plus half of x minus 3/2. Yes, so that bit here is minus x, because it's minus 2/2, which is minus x. So -1 to 0, 1/2 minus x minus 3/2 x squared integrated. So this is 1/2 x in limits from -1 to 0, minus x dx, this is x squared over 2 in limits -1 to 0, minus 3/2 x cubed over 3 in limits from -1 to 0. So this is 1/2, 0 minus minus 1, minus 1/2, 0 squared minus minus 1 squared. These cancel each other out, which is minus 0 cubed minus minus 1 cubed. And the whole lot is what? This is plus 1, so this is a half. This is minus plus a half. And then what do we have here? It is minus plus minus minus 1. Right? That's or maybe not quite. So there might be some error somewhere, because I got that to be negative, and that can't be. I got that to be 0. That can't be. All right, there is a factor of 2 which I've forgotten. Minus 1/2. So I get 1/2. Ah, that's better. Okay, so that is the area of the tetrahedron. Now, I would like to give you a list of problems. So those of you that watch the videos would benefit from that. Evaluate. Now watch the lectures on double integral. Some will be able to do that. For the region, which is the Cartesian product of the interval 0, 2 with -1, 0, evaluate A1 integral x squared y squared plus x. So this is a simple region. Then integral the absolute value of y, that's an interesting one, cosine pi x over 4 dx dy. Then integral over r minus x e to dx sine pi y over 2 dx dy. And so this is problem number 1. Problem number 2 is find the volume under the graph of f of x y, which is equal to 1 plus 2x minus plus 3y over the rectangle one, 2 cross 0, 1. Okay, so this is the end of this segment. Okay, in this segment we'll consider a very important topic. This is the so-called changing the order of integration. Now, suppose in the xy plane we are given some region D, And suppose that the topmost point of this region is there. So this is the equation of, this is the straight line with the equation y equals d. The bottommost is there. So this straight line here is say C. So this straight line is with equation y equals C. Suppose that the leftmost point here is at A. So this straight line has equation x equal to A, and at the rightmost point, so we identify the four extremes of that region, so that this straight line here has equation x equal to B. Okay, now that region D will be viewed in two different manners. So basically what we will do, we will be calculating integral f of x y over that region dA. Now let's start using dA. So dA will simply be dx dy. So this is the area element. So this is the same as integral over d fx y dx dy. Okay, now what we'll do is first, using these identification, so that is point the topmost and the bottommost. So let me use that color and the red one. To write the following. So for every, let me just get the colors right first. Then what we say is the following. This here, the yellow one, is say some function psi 1 of y, and the red one is some function psi 2 of y. So with this parameterization of the region D, the region D can be viewed as follows. For every y between C and D, for example, that particular value here, x will vary between the left function and the right function. So x will vary between the left function and the right function. Alternatively, what we'll do is, and now it's the difficult part, to plot the absolute same picture. So this is the region D again. Now, instead of identifying the leftmost and the rightmost, and the highest point and the topmost and the bottommost, let us now identify these two. So that would be A, that would be B, just like here with the green ones. Now what I will do is I will use this one. So this function and then this function, like that. So you can see that for every x between A and B, for instance, that value there, so the region D can be viewed as follows. For every x between A and b, for example, this value here, y varies between the lower function and the upper function. So the upper function is phi2 of x, the lower function is phi1 of x. So that is y varies between the lower function and the upper function, phi2 of x. So these are the two parameterization of the same region D. So you either identify the top and the bottom of that region, and then for every y between the top and the bottom, say this one, x varies between the left function and the right functions, namely this. Or you identify the left and the right, and for every x between the left and the right, y varies between the bottom function and the top function, and that is that. Okay, so therefore, what is that integral? That integral is, let me try to squeeze that here if I can. So this is equal to, now, integral, if I use this, maybe I won't be able to. Okay, you have the, I'll try to. Okay, integral from c to d dy integral psi1 of y to psi2 of y f of xy dx. So this is if we use that identification. If we instead use that identification, so let me write in green here, integral over d f of xy dA will be equal to integral over x from a to b, following integration from phi1 to phi2 f of xy dy. That is very, very simple. Okay, so this is how we change the order of integration. So on your exam, you will be given a double integral over some region, and you will be asked to change the order of integration and integrate. So you have to integrate the same twice. And let us consider examples. So you have a tutorial dedicated on these. So suppose you have the quarter circle. So this is x, this is y. This point here is 0a. So this is a quarter of a circle, so this is a0, clearly. This is a circle of radius a, so this is our region D. Okay. So find integral over D of a squared minus y squared under the root. So calculate that integral using one order of integration, then change the order of integration and integrate again. Okay, so how do we parameterize D? D can be parameterized in two different manners. So first of all, this is a circle. The equation of a circle is x squared plus y squared is equal to the square of the radius y squared. So from here, we can solve for x and write that x is, okay, x squared is a squared minus y squared, then x is plus minus x squared minus y squared. Now x is positive, right, because we are in the first quadrant, so therefore we have to discard the negative sign. Therefore this function here can be viewed as x is a squared minus y squared. So what happens for every y between between 0 and a, so for every y between 0 and a, for example this particular one, x varies between 0 and that function. So let me write that, make that clear. So the parameterization of D is as follows. For every y between for every y between 0 and a, so that is where y is, because this quarter circle is, the bottom is at y equal to 0. This line here, the abscissa is y equal to 0. The top is at y equal to a. So for every y between the top and the bottom, x varies between the left, which is 0. This one has equation x equal to 0. And the right, which is this one. So there is x varies between 0 and this guy. Let me make that thicker. Right. Like that. So x varies between there and there. And then I can finish this off here by saying that a squared minus y squared. So this is one parameterization. And therefore, our integral will be integral for every y between 0 and a, x varies between 0, a squared minus y squared, and the function is a squared minus y squared, and this is dx. Okay, so what is that? This is it's quite simply the following. So this is equal to integral 0 to a dy. Now, when you integrate with respect to x, this is a constant that can be taken outside of the integral. So this is a squared minus y squared, and then the integral from 0 to a squared minus y squared dx. This integral is simply x in the limits from 0 to the root here, and so this is simply the root minus 0, which is the root. So therefore I is integral from 0 to a dy a squared minus y squared, which is this, and we have to multiply by that, so that will be squared. So it's integral from 0 to a dy of a squared minus y squared. So this is a squared integral from 0 to a dy minus integral from 0 to a of y squared dy. So this is a squared integral of dy is y in limits a to 0. This is simply a minus y cubed over 3 in limits 0 to a. So this is a cubed minus a cubed over 3, and zero a squared minus y squared, and the function is a squared minus y squared. and this is dx. Okay, so what is that? This is it's quite simply the following. So this is equal to integral 0 to a dy. Now, when you integrate with respect to x, this is a constant that can be taken outside of the integral. So this is a squared minus y squared, and then the integral from 0 to a squared minus y squared dx. This integral is simply x in the limits from 0 to the root here, and so this is squared. So this integral from 0 to a dy of a squared minus y squared. So this is a squared integral from 0 to a dy minus integral from 0 to a of y squared dy. So this is a squared integral of dy is y in limits a to 0. Is simply a minus y cubed over 3 in limits 0 to a. So this is a cubed minus a cubed over 3, and that will be 2a cubed over 3. 2a cubed over 3. So that is the volume of the figure, which has this function as a lid and this quarter circle as base. Now what we're going to do is change the order of integration. So what I'm going to do now, and I'll probably do it on the next page, is this. Instead of solving the equation of the circle for x, like that, we're going to solve for y. So this here will be y is equal to a squared minus x squared. Again, there is a plus minus, but because y is in the first quadrant, so we drop the minus sign. And then look, x varies between 0 and a. And forever, because this is the leftmost, so this is here x equal to 0. The rightmost point is at x equal to a. For any x between these two, for example, if I take this value of x, then y will vary between this, which is y equal to 0, here on the abscissa y is equal to 0, and this function. So I can probably clean a bit. And write the following. Let me just move that. Okay. So the parameterization of D in this case will be following. For every x between 0 and a, so this is where the x's live, between 0 and a, and for everyone, for instance, if you take this one, which is between 0 and a, while we vary between the bottom and the top. So this is the parameterization of the region of integration D. And then we have to change the order of integration. So therefore, our integral I, which was integral over D of, there's no need to bracket here, integral of D of a squared minus y squared dA is therefore, look now, this is for every x between 0 and a, there you go, you have y between 0 and a squared minus x squared, and then the function is a squared minus y squared, and we integrate over y here. Now, that's a little bit awkward. This integral, you have to make a geometric substitution. Y is equal to a, for example, it is cosine of t. And so what is then dy? This is equal to d on a cosine of t, which is a, the derivative of cosine is sine with a minus sign, so it is minus a dt. Then what about that one? A squared minus y squared. That will be a squared minus a squared cosine squared of t, which will be a squared 1 minus cosine squared of t under the root 1 minus cosine squared under the main trigonometric identity is sine squared, so this is a sine of t. And the last thing that we need are the limits. So from here t, okay, for every x between 0 and a, there you go, you have y between 0 and a squared minus x squared, and then the function is a squared minus y squared, and we integrate over y here. Now, that's a little bit awkward. This integral, you have to make a geometric substitution. Y is equal to a, for example, it is cosine of t. And so what is then dy? This is equal to d on a cosine of t, which is a, the derivative of cosine is sine with a minus sign, so it is minus a dt. Then what about that one? A squared minus y squared. That will be a squared minus a squared cosine squared of t, which will be a squared 1 minus cosine squared of t under the root 1 minus cosine squared under the main trigonometric identity is sine squared, so this is a sine of t. And the last thing that we need are the limits. So from here t, okay, y over a is equal to cosine t, so t is arc cosine of y over a. So when y is equal to 0, then t is arc cosine of 0. And when y is equal to a squared minus x squared, t is arc cosine of a squared minus x squared. So upon this substitution, so this is what I'm going to write. This number goes here, this number goes here, this dy goes there, and this root, which is a sine of t, goes here to get that our integral I is integral from 0 to a dx. Integral, now cosine of 0 is pi over 2, so that will be pi over 2 to arc cosine of that function a squared minus x squared. Now the integrand, the square root, is a sine of t. dy is a sine of t dt, and there is a minus sign coming from it. So this is basically a squared sine squared of t. Now this is a bit awkward. I mean, this integral is straightforward to be calculated, but when you plug in the limits, then that will be well, not too bad, but let me show you. So we use a bit of trigonometry here. Sine squared of t is equal to 1 minus cosine of 2t over 2, right? So that our integral becomes I minus, I'll take 1/2 from here, I mean this outside there, and then we have integral from 0 to a dx, integral from pi over 2 to this horrible thing, arc cosine of a squared minus x squared, and then I'll take also a squared outside, that's a constant, and then what we have is 1 minus cosine of 2t dt. So the first one is when we integrate only that, so let's call that j. So this is integral of dt, so pi over 2 to arc cosine of that dt minus cosine of 2t d2t from 0, sorry, not 0, so pi over 2 to arc cosine a squared minus x squared. Okay, so the first integral is d in these limits, so this is arc cos x squared minus x squared minus pi over 2, and the second one is integral of cos is minus sine, so it is sine of twice 2t, which is like that, and I forgot the half there. And there is the half there, and the limits from pi over 2 and arc cosine x squared minus x squared. So basically what happens is the lower limit here is 0. So I have sine of twice the angle, it's sine of the angle times cosine of the angle. So again we have an inverse trigonometric function which we have to plug in here and integrate. I am not going to do this because it requires a substantial amount of work. So, but nevertheless, if you persist, if you integrate that until the end, and the integrals are more horrible if you go this route, you'll again get the same answer as before. Right. Okay. So let me illustrate these ideas with another example, and the other example is the following one. Calculate the volume, so basically I, so it's example number 2, is integral over d x minus 1 times y dA. So this is what we want to determine, where d is the following. Natural logarithm of x. Clearly, when x is 0, a logarithm of 0 is 1. So then this straight line has equation x equal to 2. This straight line here, the abscissa, has equation y is equal to 0. So the region D is inside here. So how do we parameterize that region? Okay, so this, let me do one of the parameterizations. So for every x between 1 and 2, that is for every x, so this is the parameterization, for every x between 1 and 2, for example there, this one, y varies between this function, or this which is 0, and this one. This function is logarithm of x. Okay. Now, that's one way of seeing things. The other way of seeing things is the same picture, now we identify the top and the bottom. So where is the top? This is 1, this is 2. This point is a logarithm, natural logarithm of 2, right? And so what is then, for every y between the top and the bottom, for every y between the bottom and the top, the bottom is 0, the top is natural logarithm of 2, x varies. So for example, if we take this value which is between the bottom and the top, so here x will vary between the left function, so this is a function of y, and the right hand. So what is that? That is x is equal to 2, of course. So x will be there. The question is, what is that function of y? Now this is the function y is log of x. This is the function x, which is e to the y. It's the inverse function. So you have to invert the function e to the y. So in this sense, our integral over d, so this is our integral, that can be written in two different ways, both yielding the same result. The first one is integral, so let me just clean that bit there. The first one is that one here. So this is equal to integral. Now x is between 1 and 2, right? And then y is between 0 and logarithm of x. So what we have is x minus 1 y dy, right? And alternatively, this will be equal to, now y runs from 0 to logarithm of 2. It is y that runs now, because before it was x that runs between 1 and 2. Now y runs from 0 and log of 2, and then this follows integration of e to the y to 2, because this is where x varies between e to the y and 2, of the function which is x minus 1 y dx. So the idea is to solve this integral, and to solve this integral, that's called reversal of the order of integration, and these two will turn out to be equal. Of course they are equal, because how we parameterize d, it doesn't matter, for as long as it is the correct parameterization. So whether this or this, these are the two parameterization of the same region, they will yield the same result. So there will be a tutorial on that, especially dedicated tutorial where more problems will be addressed. So I'm not going to do these integrals. They're straightforward, because this is an integral of a function of a single variable. Then we integrate again. This is again a function of a single variable, which we integrate again. Okay, so this is the end of this segment. Okay, in the next lecture we continue with the problem that we were doing last time. I thought of leaving that to you, but upon second thoughts, I think it'll be probably a better idea if I solve that again. So I mean, if I solve that until the end. Now, there are the two parameterizations of the region D, the region of integration D. So this is the region D here, and this is the same region again. So this is the same picture. These two pictures are the same, but there will be different perspectives on them. Now let me get rid of the yellow marking. So I'll continue with. So let's continue with the first parameterization. I'll use purple for that one. Know that for every x between 1 and 2, so where is x equal to 1? It is here. For every x between 1 and 2, so x is 1 at that point, x is 2 at that point. Say, for example, for this value of x, which is between 1 and 2, this one here. So for every x between 1 and 2, y varies between 0. So y varies between 0. So here, this one is y is equal to 0. And logarithm of x. So this is where y varies between 0 and the graph, which is a logarithm of x. So that's embedded here. For every x between 1 and 2, y varies between 0 and the logarithm of x. Right. Now, likewise, in the second problem here, we have in the second parameterization here, we have for every we identify the bottommost and the topmost points of your region. So these are 0 and log of 2. So for every y between these two, let me again, it will be green one, sorry. For every y between these 2 points, between 0 and between 0 and log of 2, for example, this one here, then what you have is that x varies between the graph of the function and this. So this one here has equation x equal to 2. Now the graph of the function is now a function of y, so that is the inverse function. These two functions, log of x and e to the power of y, are a function and its inverse. So if you put instead of x, you put log e to the y, you get y is log of e to the y, which is simply y, or alternatively, if you put instead of y there, you put log of x, you have e to the power of log of x, which is x, so function and its inverse. When you reverse the order of integration, you have to make sure that you also invert the function. So there it is. For every y between 0 and 2, for every between 0 and log of 2, then x varies between e to the y there and 2 there. So these are two separate integrals, and I will do both of them, and let's see that you should get the same results. So, I mean, they're much longer than the space I have for these, so I'll just prepare the stuff before I address them separately. Now, note this integral here is an integral over y, and x minus 1 is a constant of integration, which can be taken outside. So you have integral from 1 to 2, but outside the first integral. The second integral is over x, so this is no longer a constant. So you have the x, you can't take x minus 1 outside this integral. And then in here you have integral from 0 to log of x of y dy. Now what is integral of y dy? It is y squared over 2. Right, so this integral is then, let me write the first one as it is, then we have x minus 1. Integral of y dy is y squared over 2, and the limits of integration are 0 and log of x. So here you have log of x as the upper limit. I have no room to. So this is equal to 1/2 integral from 1 to 2. Now this 1/2 of which I've taken outside, and then you have, when you plug in the upper limit and open the brackets at the same time, so it will be x times log of x, x log of x, and that log will be squared because y is squared, dx, minus the same 1/2 integral from 1 to 2, and then you have 1 times log of x, log squared of x, so it will be log squared of x, so it's jumpy, log squared of x dx minus 0, but I mean 0 times anything is 0. So there are two integrals here. Let me call this one, so let's call this one j, let's call this one k. So therefore I is j minus k. So before doing number 2 here, I will do I, which is j minus k, on a separate page. Okay, so j is 1/2 integral from 1 to 2 x log squared of x dx. Now, what I'm going to do here is, just as an aside, I'm going to integrate by parts. And I'm sure you know the formula for integration by parts. If you have integral of a function d another function, that would be the product of the functions minus integral, write d. Now the function that was behind, g, goes in front. The function that was in front goes behind the differential sign, so that's g df. Now what I'll do is I'm going to prepare this, so I'm going to bring x inside. So how do I do that? Recall the first fundamental form of calculus, or the first differential of the function h of x. If you have a function h, then dh is h prime of x dx, where h prime is the derivative. Now if you divide both sides by dx, what you get is something that you are very familiar with, dh dx, so that is the derivative of the function. Okay, so when you have d, let's see, this function is behind d, and this function has popped out and it has been differentiated. So when you have d, on the way out of d, that is, if you bring functions out, you differentiate that. For example, d on cos of x is the derivative of cosine times dx. The derivative of cosine is minus sine, so it is minus sine of x dx. Also, d on x cubed will be the derivative of x cubed dx. So the derivative of x, the derivative, beg your pardon, not squared, the derivative of x cubed dx, and the derivative of x cubed dx, the derivative of x cubed is 3x squared dx. Okay, so how about bringing stuff in? For example, if I have d, how do I put functions inside? It is very simple. It's anti-differentiation, or this is the same as integration. So it's an integral within the integral. For example, what we have here is x dx, and x dx is, now we're looking for the function whose derivative is x. Clearly, to find the antiderivative, you need to integrate. So this will be equal to d. Integral of x dx is x squared over 2. And this is what we have, x dx. So that will be, this 1/2 is this 1/2, so it doesn't there. So it will be log squared of x dx squared over 2. And now we integrate by parts, so it's 1/2. Now the product of the two functions, that's one function, that's the other function. So like here, f dg, so that is your f, that's your g. You have f dg, so it's log squared of x times x squared over 2 in limits from 1 to 2 minus this 1/2, which is just an overall factor, minus integral from 1 to 2. Now the function that was in front goes in the back, and the function in the back goes in front, d log squared of x. Now, what's that? You plug in the limit, so you have 1/2 log squared of 2 times 2 squared over 2 squared is 4, 4 over 2 is 2, minus. Now you plug in x equal to 1. Log of 1 is 0, so the whole lot is 0. So that is that cancelling that, so just log squared of 2 minus 1/4, a half by a half, integral from 1 to 2 x squared. Now this logarithm I'm going to regurgitate in front of d, so I have to clearly differentiate that. So what is the derivative of log squared? It's a function of a function. The outer function is raising to the power of 2. The derivative is twice the argument. And then you have to multiply by the derivative of the inner function, which is the derivative of log, that is 1 over x. So the thing becomes log squared of 2 minus 1/4 times 2, so it'll be just a half. 1/2, because 2 over 4 is a half. X squared over x is x log of x dx, and the limits are from 1 to 2. So again, what we'll do is we'll rinse and repeat. Bring x inside. So this is equal to log squared of 2 minus 1/2 integral from 1 to 2 log of x d x squared over 2. And again we integrate by parts. We have a function d, another function. So this is log squared of 2, that's that part, minus 1/2, the product of the two functions. So it's x squared over 2 and log of x in limits from 1 to 2, minus, on minus there'll be plus a half integral. Now x squared over 2 goes in front, and in the back you have log of x. So this gives us log squared of 2 minus, now put in 2 for x, so you have 4 over 2, which is 2, 2 over 2 is 1, so it's minus log of 2, and then you have log of 0, the whole log of 1, which is 0, so it's 0, and then you have plus 1/4 integral. The integral is from, I've forgotten the limits, from 1 to 2, integral from 1 to 2. Now 1/4 because a half by a half, and then we have x squared. I'm going to bring the logarithm outside, and if I bring it outside, I need to differentiate that. So that would be the derivative of log of x, and this is x squared. The derivative of log of x, brackets are not good here, x squared, the derivative of log of x dx. So this is derivative, and this derivative is 1 over x, right? So this derivative is equal to 1 over x. So this is then a log squared of 2 minus log of 2 plus a quarter integral of x squared over x, which is x dx from 1 to 2, and that would be, okay, this is x squared over 2, sorry, yeah, x squared over 2, so that is a log squared of 2 minus log of 2 plus 1 over 8 of x squared, so x squared in limits from 2 to 1, or rather from 1 to 2, x squared in limits 1 to 2. So this is 2 squared minus 1 squared, which is equal to 3, so it's 3/8. So this integral here, that number here, is 3 over 8, this last number here, so that the integral j is log squared of 2 minus log of 2 minus log of 2 plus 3 over 8. Okay, now let me do the integral k. Recall k was 1/2 integral from 1 to 2 log squared of x dx. Again, we have a function d, another function, so we integrate by parts the product of the two functions. The function behind d is x, the function in the front is log squared. These are in limits from 1 to 2 minus 1/2, the overall factor of 1/2. Then you have integral from 1 to 2. The function that was at the back, x, goes in front. The function that was in front, log squared, goes in the back. Right, so log squared. Now plugging the limit, so you have 1/2 times 2 times log squared of 2 minus log of 1, which is 0, so then you have minus 1/2 integral from 1 to 2 x. Now bring this outside by differentiating it. Log squared of x needs to be differentiated if it is to be brought outside. Now what's that derivative? That's twice log of x times 1 over x. So the whole lot becomes 1/2 over times 2 is simply 1, so it's log squared of 2 minus 1/2 times 2 is 1, so you have integral from 1 to 2, x over x is 1, so you have log of x dx. So this is a log squared of x minus, okay, you have a function, the another function, so it's x log of x in limits 1 to 2 minus and minus plus, and then you have integral of x d log of x. The functions trade their places like that. So here you have a log squared of x minus 2 log of 2, then log of 0, log of 1 is 0, and then you have plus, bring this outside, that means you have to differentiate it, log of x dash dx. Log of x dash is 1 over x, x over x is 1, so the whole lot is log squared of x, that is log of 2 here, log of 2 like that, minus 2 log of 2 plus integral of dx from 1 to 2, and this is simply x in limits 1 to 2, and this is 2 minus 1, and this is 1. So this is log squared of x minus 2 log of 2 plus 1. Okay, so I is j minus k. So j is from the previous page, I'll fetch it now. So this is log of, not log of x, what am I writing? It's log of, that is 2. So that should be 2. 2, there's no x, it can't be x when you integrate over x. So that will be log squared of 2 minus 2 log of 2 plus 1. And now from the previous page we have the expression that we got for j is the following one. So I had to change screens here to see. So that is log squared of 2 minus log of 2 plus 3 over 8. So this will cancel this, minus 1, and there is 4 from there, so it looks like 3. So this is 4 minus 1 is 3, so 3 log of 2, 3 over 8 minus 1, which is 8 over 8, minus 5 over 8. So this is what we got following the first path. And I just noticed a typo here. Actually, let me correct it before it's too late. So this is there, minus 2 with minus plus, so it's 2 minus 1. This is 1. It's not 3. This is just, so the answer here is log of 2 minus 5 over 8. And this is what we are going to look for when we calculate using the other parameterization. That is, when we reverse the order of integration, namely when we do this, and I'm going to do this now. So this is what needs to be done. I'll do it on a new page, and let me do that. I'll rewrite that on a new page. Okay, so let me write I. That's the other parameterization of the region of integration. That is integration with reversed order. So y runs now from 0 to logarithm of 2, and x runs from, for every y between 0 and log of 2, x runs from e to the y and 2, as we discussed. And then the function that we have is this one. Now integrate over x. When you integrate over x, y is a constant, so you can take it outside of the integral over x to get integral from 0 to log of 2, and then we have dy, and then y integral e to the y to 2 x minus 1 dx. Alright, so with the brackets here. So that here is integral from 0 to log of 2 dy, and then you have y. Now integral of x, the x is x squared over 2. The limits are e to the y to 2, minus integral of the x is simply x in limits e to the y. Namely, when we do this, and I'm going to do this now, so this is what needs to be done. I'll do it on a new page, and let me do that. I'll rewrite that on a new page. Okay, so let me write I. That's the other parameterization of the region of integration. That is integration with reversed order. So y runs now from 0 to logarithm of 2, and x runs from, for every y between 0 and log of 2, x runs from e to the y and 2, as we discussed. And then the function that we have is this one. Now integrate over x. When you integrate over x, y is a constant, so you can take it outside of the integral over x to get integral from 0 to log of 2, and then we have dy, and then y integral e to the y to 2 x minus 1 dx. Right, so with the brackets here. So that here is integral from 0 to log of 2 dy, and then you have y. Now integral of x, the x is x squared over 2, the limits are e to the y to 2 minus integral of the x is simply x in limits e to the y to 2. So this is integral from 0 to log of 2. Integral is over y, and what we integrate is y. Now we plug in the upper limit, so this is 2 squared. So 2 squared over 2 is 4 over 2, or simply 2, minus e to the 2y over 2, so it's 1/2 e to the 2y, and then there is y here outside. This way, and then minus the other one, 2 minus e to the y. This is minus, and you close that bracket. Okay, so what do we get is 2 minus 2 is 0. Right, so dot would cancel dot, so you have 0 to logarithm of 2, and then the first integral is that minus 1/2. I'll take outside brackets, minus 1/2 outside of the integral, and then inside you have y e to 2y dy, and then you have minus on minus, which is plus, and that plus comes with e to the y e to the y e to the y dy, and the integral is from 0 to natural logarithm of 2. Okay, so let me call this integral p. Let me call this one q. So I, which is the original integral but with the reversed order, will be p plus q, where p is minus 1/2 integral from 0 to log of 2 y e to 2y dy, and q is integral from 0 to log of 2 y e to the y dy. Okay, let me do them separately. So p is minus 1/2. What I'm going to do is, note we have 2y there, so what I'm going to do is I'm going to divide by 4 and multiply by 2 twice, so that'll be log of 2. That's the first multiplication by 2. It was y, now it's 2y. d to 2y here, d 2y. So this 2y suggests to write 2y everywhere. So that is then minus 1 over 8. And I'm going to bring this function in, so that will be integral from 0 to log of 2 of 2y e to dE, beg your pardon, dE to the power of 2y. We integrate by parts, so it's minus 1 over 8, 2y e to 2y. That's in limits from 0 to log of 2, minus 1 minus, plus then 1 over 8 integral from 0 to log of 2. The function that was at the back, e to 2y, now goes in front. The function that was in front goes in the back, d to y. So continuing here, this is minus 1 over 8. Now plug in the upper limit, so you have 2 log of 2. Then you have e to the power of 2 log of 2 minus 0. So let's not bother with that. So that, because if you put 0, then the whole plot will be 0. Now what is e to 2 log of 2? So this only is equal to e to log of 2 squared, using the properties of the logarithmic function, which is equal to e log of 4, and this is 4. Right, and then the other integral is plus, sorry, 1 over 8, 0 to log of 2. Now actually this is a table integral, so let's not write it, let's just do it directly, and this will be e to 2y in limits from 0 to log of 2. So what do we get from the first one? So we have 4 times 2 over 8, which is 1, so we have minus, that whole lot is logarithm of 2, right? And then we have plus 1 over 8, and here you have e to the power of 2 log of 2 minus e to the power of 0. Now as we saw, this is 4 there, so this is 1. So inside the brackets we have 4 minus 1, that is 3, so this is minus log of 2 plus 3 over 8. So this is this integral p. Now what we have to do is the integral q. So I'll rewrite it on a new page. So here it is, q. It's integral from 0 to log of 2y e to the y dy. This is very easy to integrate, so bring e to the y inside. The derivative of e to the y and integral of e to the y is e to the y, so it's e to the y. Integrate by parts. The two functions are y e to the y, that product in limits from 0 to log of 2, minus integral from 0 to log of 2. The function in the back goes in front. It is, beg your pardon, it is e to the y. The function that was in front goes in the back, the y. And this is a table integral. Right? So let's continue. So plug in the upper limit, log of 2 times e to log of 2 minus 0, because when you put 0 here, you get 0. E to the power of log of 2 is 2, minus, that is the table integral, it's e to the y in limits from 0 to log of 2. To log of 2. So from the first one we have 2 log of 2 minus, now e to the power of log of 2 minus e to the power of 0. E to the power of log of 2 is 2, this is 1, so 2 minus 1 is 1, so this is 2 log of 2 minus 1, so that's q. Now I, if you remember, was equal to p plus q. Now p plus q, so plus, this is q, log of 2 minus 1, and p from the previous page, so this is p minus log of 2 plus 3 over 8, minus log of 2 plus 3 over 8, 3 over 8, this is minus 1. Okay, so you have 2 log of 2 minus log of 2, this is once log of 2, And then you have minus 1, which is 8 over 8, plus 3, so it is minus 5 over 8. And this is exactly the same answer as we got before. So I told you that the integrals are not that difficult. These are considered as quite simple integrals. And so I've done the integration by reversal of the order of integration in full. So this is the end of the problem that we considered at the end of the previous lecture. The next topic that we'll consider is the triple integral. So suppose we have a function f, which is a function of x, y, and z, over the box B, which is the Cartesian product of three intervals. Namely, the first variable x varies between a and b, the second variable y varies between c and d.
This guy's gonna
and the third
fucking do
variable
triple integrals
z
now.
varies
I
between c
swear to God.
and q. So what I'll do is I'll plot these. Okay, so here's our three-dimensional Cartesian coordinate system, x, y, and z. So the three variables of the function f are along the three coordinate axes. Fortunately, we can't plot the function because for that we need a fourth dimension and we can't visualize that. So we know that for every point in our three-dimensional space, every point characterized by the order triple x, y, z, we have a value of that function, if the function is defined everywhere, of course. So now let me mark. So on the x-axis, x is allowed to vary between, let's say, just different color. Use different colors, that'll be better. So on the x-axis, x is between a and b. Suppose they're positive. Suppose all that positive. So x varies there. So what we'll do is we'll draw lines that are parallel to the y-axis and parallel to the z-axis through these 2 points, A and B, like that. So basically what I'm getting at is a rectangular parallelepiped, right? So that's that, down, that goes up, like that. Now C and D are along the y-axis. So that's C, that's a C and D. And y is allowed to vary here between them. So between C and D. So that's the second integral in the Cartesian product. Again, we draw lines perpendicular to the other coordinate axis through these points, like that, and then like that. And then from these two and these two, we draw up. So z varies between p and q, so let me mark here p, and let me mark here q. So z is allowed to vary between p and q, there. So we draw lines parallel to the x-axis through that point, p, along the z-axis, and then as well through q, and then lines parallel to the y-axis, there, and there, like that. Then through these lines parallel to those ones, like that, and likewise here, so that we end up with a parallelepiped, and this parallelepiped is okay. So these two have to make that. Then it's too long, like that. So you get the picture. That is our parallelepiped from there.
No, I don't get the picture. The fuck did you just draw? Parapiped my ass.
There. Okay, so this is our box B. Inside, so x varies between A and B. Okay, this is the x-axis. X varies between A and B. Y varies between C and D. So this is where x varies from there to there, right? Y varies from there and there. So this is the base, and Z varies between P and Q. So this is the actual the tick on there. Alright, so that is the actual. Let me change the color to this one. That is the actual box. Rectangular parallelepiped. Like that. Okay. Now, what we need to do next is partition B into n equals sub-boxes. Okay, and let's say that it's n by n by n because it's a 3-dimensional, so it's n cubed equals sub-boxes. So there is a row of boxes along the y-axis, n, a row of n boxes along the x-axis, and a row of n boxes along the z-axis. So let's call each sub-box B, I, J, K, where each of these numbers, I, J, and K, runs from 1 to n. So basically it's very simple. That is the base partition into squares, and then you put a new row of squares on top, a new row of squares on top, like that. So there is n squares in that direction, n in that direction, and n in the vertical direction. So then one of these boxes,
Seriously, this guy.
throw it here, so inside here, this is one such small box, right? So this is B, I, J, K. Okay, so let us choose next point C, I, J, K in that little box B, I, J, K. So in here, inside somewhere is the point CIJK. So it's a point from within that box. Okay, what is the volume? The volume of BIJK. So the volume of the box, or the sub box rather, the sub box BIJK is delta V, which is delta X by delta Y by delta Z. So if I take this box B and I draw it separately like that, and zoom in a little bit, like that. So this is along the x-axis here, this is along the y-axis, and this is along the z-axis. So this length from here to here is delta x, this length from here to here delta y, and this length from there to there delta z. So the area of the base is delta x delta y, the area of the height, the height is delta z, so the volume delta v is delta x delta y delta z. Now I'm going to erase this part because I need to make a definition. So, okay, that box will also get erased. Okay, so the definition of the triple integrals is as follows. So I write here definition. Let f be a bounded function. Bounded means it never goes to infinity. A bounded function of 3 variables say x, y, and z, defined on the box B, which I erased, which is this Cartesian product of 3 intervals. If the limit I running from 0 to 1, j running from 0 to 1, k running from 0 to 1, f of c I, j, k multiplied by delta v exists and is independent on any choice of c, I, j, k, we call f integrable and if the limit, I forgot to write the limit here, that we have limits and approaching infinity. Right? That's the limit, because without that it wasn't a limit. We call f integrable, and we call this limit triple integral of f over b. And we write integral
Looking for a
b
result.
f dv. Now, when you see that, that's actually triple integral. So this is the same as integral over b. It's a triple integral f dv, which is the same as integral triple over b f dx, dy, dz. So quickly here to make an analogy to simple integrals.
Fuck you and your
double
fucking
integrals and triple
simple.
integrals. We call a simple integral
They're
is
not
the area
simple
under the
at all.
graph. So if you have a function like that,
Wait.
the area under the graph of the function is integral of that function from a to b. Now, if you have a function of 2 variables, what you have is a surface, which is the function, that's when it's plotted in 3 dimensions, and the double integral is the volume of the figure obtained having the surface, which is the graph of the function, and as its top. Now, so if you go from a function of 1 variable to a function of 2 variables, you see how areas become volumes. Now, if you keep going, and then you include a 3rd variable, now we can't plot that because we need the 4th dimension, as I mentioned earlier. And so what we need to interpret, the way we need to interpret the triple integrals is as follows. It is the generalization of the concept of volume. But we can't generalize that again because we are 3-dimensional creatures and we can't see into the 4th dimension. So just like here, an area for a function of 1 variable, area under the graph, which is the integral of the function, became a volume under the graph of the function of 2 variables. In the same way, when a function of 2 variables is generalized to a function of 3 variables,
Why
then
are
the
we even
volume has to be
studying this
generalized to the next object. So you see area goes to volume, volume goes
I
to
can't even
the
see
next
the dimension.
generation of volume, the four-dimensional concept of this. So this is what the your integral, triple integral represents. Now this here is nothing else but the Riemann sum of the function f, and just as I introduced that for a function of a single variable, for a function of two variables, in the exact same way it is generalized to a function of three variables. And you can continue that. You can consider a function of four variables that you need, then you need a five-dimensional space to plot it, and then you have to generalize the generalization of volume into into five dimensions, and so forth. Okay, so how do we link the triple integral to iterated integrals? So that's our next reduction to iterated integrals. That's the next topic. So consider that our function f again over the same box, which is the integral close interval ab, that's where x lives, with cd, that's where y is, and then pq, that's where z is allowed to vary. And then let f, so that's how we do this integral. So this is the box, and f, which is a function of x, y, and z, let that function be integrable on B. Then any iterated integral that exists is equal to the triple integral. Integral, triple integral over B of f of x, y, z dx, dy, dz is integral from P to Q, integral from C to D, integral from A to B. Now, note we have x, y, z. Now it doesn't matter in this particular case over which you integrate first. So how many possible orders we have of these three? That's 6, because 3 factorial is 6. So x leading y, z, z, y, then y leading x, z, y leading z, x, and then z leading x, y, z leading y, x. So, for instance, if we integrate over x first, then over y, then over z, so we have x, y, z, the first one, so first integral is over x, and then we have our function f of x, y, z. So integrate the function with respect to x first between a and b. When you integrate that, x will disappear because that's a definite integral over x. This will be a function of y and z. You integrate over y, that it means that y will disappear because it's a definite integral with respect to y. And then that will be a function of z, which we integrate, and then it will give you a number, which is that four-dimensional volume. Alternatively, you can write, instead of x, y, z, you can write, for instance, this one. You integrate over y first, y lives between c and d. Then you integrate over z, which is between p and q. And then lastly you integrate over x, which is between a and b, and you integrate the same function again. So etc. I write etc. here because there's six possible orders of integration. So 6, I've written 2 of them, DAY, which resolves the remaining 4. It is absolutely straightforward. And
Fuck you and
now
you're
consider
straightforward.
examples.
I'm going straight
Example.
backwards in my evolution. How about that? So fucking gay.
Be the box 0, 1, Cartesian product with minus 1 half 0, Cartesian product with 0, 1 third. Evaluate. So evaluate integral over this box of the function x plus 2y plus 3z squared dx dy dz, and b show that we get the same answer if we integrate in order y, z, x. So what's the order here? This is x, y, z. So here the order is x, y, z. Okay. Alright then. So let me solve this problem. Actually, I will do that in the next segment. Okay, in the next lecture segment, let's
fuck?
solve this. Just switch back to work. So we start with
It's fucking 1
A.
hour.
We have to evaluate in the order first x, then y, then z. So, and let's call this integral I. So I is, I'll use a friendlier way of writing. So it will be first, it will be integrated over x, and x runs there from 0 to 1. Then afterward, the output of that integration will be integrated with respect to y. Y runs between minus a half and 0, and finally we'll integrate over z, and z is afterward, the output of that integration will be integrated with respect to y. Y runs between minus a half and 0, and finally we'll integrate over z, and z is allowed to run between 0 and 1/3. Okay, and then the function that we integrate is x plus 2y plus 3z the whole squared. Okay, what I'm going to do now is note that when we integrate with respect to x, y and z are constants. So for that reason, I'm going to change the measure of that first integral. Integral is from minus 1/2 to 0 dy integral. Now x plus 2y plus 3z squared is our function. The integral is over x between 0 and 1. What I'm going to do here is I'm going to change x to x plus 2y plus 3z. Why I added that? Because I can, and I can do that for free, because as I mentioned, 2y plus 3z is a constant. Then b, which is derivative, the derivative on a constant is 0. So for that reason, and I'll just write here, because dx is the same. same as dx plus any constant c, right? And that constant c in particular can be 2y plus 3z, right? Because when we integrate with respect to x, every other variable is frozen. That is, it is a constant. Then that is integral from 0 to 1/3 over z, integral from minus 1/2 to 0 over y, and then what we have is, think of this expression x plus 2y plus 3z, think of that as being t. So effectively we do change variables without doing change variables. So this is t squared dt. What's integral of t squared dt? It is t cubed over 3. So instead of t cubed, I'm simply going to write what t is equal to. It's x plus 2y plus 3zx plus 2y plus 3. Sorry for squeezing that here. So x plus 2y plus 3z to the power of 3 over 3. And here x varies between 0 and 1. So let's put in the limits. So it's integral from 0 to 1/3 over z, following integral from minus 1/2 to, so you read this right to left, that's where this integral follows, dy of, now you put in first the limit, upper limit, so it is 1 plus 2y plus 3z to the power of 3, and I'll take 1/3 outside of brackets. Actually this is 1/3, which I can take outside of all integrals even, and then you put in the, so that's with the upper limit when x is 1, so it becomes 1 plus 2y plus 3z, and then minus the lower limit, which is 0 for x, plus 2y plus 3z cubed. Okay, so what's that? That is 1/3 integral from 0 to 1/3. Sorry, it's very jumpy for reasons unknown. 1/3 z. Now integral over y is from minus 1/2 to 0, and then what we have is, actually there's a difference. So the integral over y is difference of two integrals, so I can, well, let me write it first as a difference, integral of a difference, and then as a difference of two integrals. Actually that is written, so maybe I should directly write like that. Integral over y, so the first term, which is 1 plus 2y plus 3z, that's to the power of 3, minus integral from minus 1/2 to 0 dy of, the integral here is 2y plus 3z to the power of 3, and to close that bracket. So note, the integral over y is integral of a difference, and I write that as difference of integrals over y. Okay, so continuing on the next page, just as we did here when we integrated with respect to x, we added a constant. I'm also going to add a constant, but I have to make sure that I do have the same, so this is 2y there, so I have to make sure that I do have the same, so it is d2y. Okay, and then I'm going to add this constant term. Okay, so on the next page, I'm going to rewrite that. So on the next page, this is equal to 1/3 integral. The integral over z is from 0 to 1/3 z, and then we have this integral over y. So the first of all, let me copy it and then explain. Okay, here it is. I wrote it on the pre-wrote it from the previous page. So So what I'm going to do here, because I have 2y, I'm going to multiply and divide by 2 here, and likewise here, because we have 2y. So this is equal to 1/3 integral from 0 to 1/3 over z applied to integral from -1/2 to 0, 1 plus, or rather, let me write 1 plus 2y suggestively as 2y plus 1 plus 3z. So just swap the places of these two. Cubed d2y. And because I've multiplied by 2, let me divide by 2. And the same goes with the other integral. I multiply and divide by 2, take the half outside, so it'll be minus integral from -1/2 to 0 of 2y plus 3z cubed d2y. Now, both here and here, I'm going to change this to d. Now, when we integrate over y, 1 and z are both constant, so this will be d2y plus 1 plus 3z, and this here will be d2y plus 3z, so that I match what's in front. Okay. So, in this sense, we'll have 1/3 by 1/2 is 1/6 integral from 0 to 1/3 dz. Now we have, think of 2y plus 1 plus 3z as u, so I have u cubed du. U cubed du is u to the power of 4 over 4 in limits from -1/2 to 0. That's the first integral. Minus, here you have again u to the power of 4, but it's a different u. It's not plus 1 there, it's just without it. So it's 2y plus 3z to the power of 4 over 4 in the same limits from -1/2 to 0. And it is y that has to be plugged in, in these limits. So this will be 1/4, so 4 times 6 is 24. Integral from 0 to 1/3 dz, and then when y is 0, so let's put in the upper limit. When y is 0, we have 1 plus 3z, 1 plus 3z to the power of 4, right? And minus, when y is -1/2, you have 2 times -1/2 is -1, -1 plus 1 is 0, so you have 3z.
Just 1 second, I need to fucking check something. Integral of 2y plus 1 plus 3z all to the power of 3 in respect to dy. I'm fucking serious. The way he does it is actually easier. Question mark. Right, so what does he do? He takes the 2y, puts it into dy, then he has to divide by 2, because he multiplies by 2. That is confusing as fuck.
To the power of 4, like that. Then that's from the first, so maybe I should put brackets like that. That's from the first expression here. Then from the second, you put in the upper limit, you have 3z to the power of 4 when y is 0. So this quarter has gone out. And then minus, you put in the lower limit, which is minus a half. 2 times minus a half is minus 1. So you have 1 minus, minus 1 minus 1 plus 3z to the power of 4. Like that. So this is equal to 1 over 24
Where's the...
integral from 0 to 1/3. So let's see what we have.
Oh, you took it out.
Here we have 3z plus 1 to the power of 4, 3z plus 1 to the power of 4. This is this term. Then this one and that one, so it is minus, so 3 to the power of 4 is 81, and it's times 2, 162 z to the power of 4, right? And then you have minus 1 minus is plus, so this would be plus.
What did you just fucking do? $162 z to the power of 4. Where'd you get the 162 from?
This one and that one, so it is minus, so 3 to the power of 4 is 81, and it's times 2, 162 z to the power of 4,
3 to the power.
right? And then you have minus 1 minus is plus, so this would be
Oh.
plus 3z minus 1 plus 3z to the power of 4. I can change the sign inside because it's raised to an even power. So that is that. And that whole thing is integrated with respect to z. Right? And now it's an integral, so it's like 3 integrals here. Right? And if you do these integrals, you have 1 over 24. Now what I'm going to do, I have 3z from this one. Okay, let me. So note, integral of I need a letter y. No, y, x, y, z are not good. Alpha. Alpha to the power of 4 d alpha is alpha to the power of 5 over 5. Right? So that's a table integral. So that's it. So let me write these as 3 separate integrals. So I'll continue on the next page. So we have 1 over 24. 1 over 24 integral from 0 to 1/3. Then we have 3z plus 1 to the power of 4 dz. minus now we have 162 over 24 integral from 0 to 1/3 z to the power of 4 z, and then we had plus 1 over 24 integral from 0 to 1/3 3z minus 1 to the power of 5 dz. So just a quick look, count for some reason. Okay, there. Very quick look. So that is 162 over 24. Very good. So with a minus. Yes. Okay. So in here, I'm going to multiply and divide by 3. So it's 1 over 72. 1 over 24. Beg your pardon. 1 over 24. Now, it will be 1 over 72, but one step at a time. So 3z plus 1 d. Now I have 3z here, so let me multiply by 3. Right? So I've multiplied by 3, so I have to divide by 3. So that's what 74. And I can add any constant here, so it is plus 1, and this is to the power of 4. Minus 162 over 24.
I can add any constant.
Z to the
Okay,
power
just
of 5
add
over
it then.
5 in limits from 0 to 1/3.
What? Oh, he just integrated.
Plus 1 over 24. Likewise here, we have 3z minus 1 to the power of 5 d. I multiply z inside by 3, so I have to divide by 3 immediately. And then I'm going to subtract 1. Again, I can do that because the derivative on a constant is 0. Okay, so this is 1 over 72. 3z plus 1 to the power of 5 over 5. Recall alpha to the 4, the alpha is alpha to the 5 over 5. And limits from 0 to 1/3 minus 162 over 5 times 24 is 20. Z to the 5 and limits there. Plus 1 over 72. And the interval is now done. It is 3z minus 1 to the power of 5 over 5 and limit 0 to 1/3. So this is 1 over 72.
Isn't that supposed to be 6?
Now put in the upper limit. 3 times the 30 is 1. 1 plus 1 is 2 to the power of 5. So 2 to the power of 5 is, so 2 squared is 4, 2 to the 4 is 32 over 5, minus, when you put the lower limit, so it'll be 1 to the power of 5, so it's 1/5, minus 162 over 120, 1/3 to the power of 5, so 3 to the power of 5, that is 243, minus 0, plus 1 over 72. I put in the upper limit, so you have 3 times 30 is 1, 1 minus 1 is 0, minus the lower limit, so it's minus 1 to the plus 1/5. Right, so you can, I'm sure you can all calculate that, and the answer that you get is actually 1 over 12. You can check on that. Okay.
Can't be. made a fucking mistake, bruh. So it should be 1/72 upper limit. So it's 3 1/6. I think it's just 1/6. Oh, it's +6 then. Because it's even. I'm close. I'm so close.
Okay, so that would be the first. Now we have to do part B. Let me use different color for it. So part B is to reverse the order of integration and to integrate with respect to y, then z, then x. So x is the last one, z is the second last, y is the first integral. Recall that y varies between -1/2 and -1/2 and 0. Z varies between 0 and 1/3, and x varies between 0 and 1. This is our box, and this is the same function x plus 2y plus 3z squared. So if you integrate over y, first of all I'm going to make sure that I have y here, I have 2y, so that's 1/2 integral from 0 to 1 over x, integral from 0 to 1/3 over z, and then the integral over y is x plus 2y plus 3z, the whole lot squared. So integral over y is from -1/2 to 0, and then we have d. I've divided by 2, so let me multiply by 2. So this 2y, that's the reason why I multiplied and divide by 2. And then note that x and z are constants when it comes to integration with respect to y, so I've just added that constant there. Oh, sorry, not square, but just added that constant. So we have integral of the type t squared dt, which is equal to t cubed over 3. So this is equal to integral, so 1/2 times 1/3 is 1/6, integral over x from 0 to 1, integral over z from 0 to 1/3, and then the integral over y is x plus 2y plus 3z to the power of 3, and I've taken the third outside. And the limits on this are, now y is minus a half. Well, clearly there's no need to write y. Zero. So when you plug in these limits, you get 1/6 0 to 1 over x, 0 to 1/3 is integral over z. So this is the integration with respect to y. So I've just added that constant there. Oh, so no square, but just added that constant. So we have integral of the type t squared dt, which is equal to t cubed over 3. So this is equal to integral, so 1/2 times 1/3 is 1/6 integral over x from 0 to 1, integral over z from 0 to 1/3, and then the integral over y is x plus 2y plus 3z to the power of 3, and I've taken the third outside. And the limits on this are, now y is minus a half. Well, clearly there's no need to write y. This is clear that it is minus a half to 0. So when you plug in these limits, you get 1/6 0 to 1 over x, 0 to 1/3 is integral over z, and then what we have is you put in the upper limit first. Y is 0, so you have x plus 3z cubed minus, and then you put in the lower limit instead of y. You have x, 2 times minus a half is minus 1, and then plus 3z, and that is cubed. Now we integrate with respect to z, so I can immediately note, first of all I'm going to make this, I'm going to change to the 3z, so I have to multiply and divide by 3. This I get 1, 6 times 3 is 18, integral from 0 to 1 dx, and then we have integral from 0 to 1/3 of the following. So first of all, we can do that immediately. So this is this integral of a difference, so therefore it's difference of integrals. So this is integral of x. Again, went the wrong way. Right, like that. So the first one is x plus 3z. So I've written, instead of z, I've written d3z. So we have x plus 3z to the power of 3 d. Now we had 3z already because of that, and I can add x to it because x is a constant when you integrate with respect to z, minus integral from 0 to 1/3. So note, the integral of a difference I write as difference of integrals. Then we have x minus 1 plus 3z cubed d. Now we have 3z here as well, and I'm not going to add x and subtract 1 so that I match exactly what we have here. So this is 1 over 18. Now this will be integral of u cubed du, which is u to the power of 4 over 4. 4 times 18 is 72. And then we have integral from 0 to 1 over x, and then the first one is x plus 3z to the power of 4 over 4, but I've taken it outside. That's in limits from 0 to 1/3 minus, now from this integral we have x minus 1 plus 3z to the power of 4 in limits from 0 to 1/3. Now, when you plug in the limits, you have 1 over 72 integral from 0 to 1 dx. Now, when z is equal to 1/3, you have x plus 1 to the power of 4, then minus, so that's when you put this, 3 times 1/3 is 1. When you put 0, you have minus x to the power of 4 from the first one. From the second one, you have x, so you put, instead of z, you put 1/3, so you have 3 times 3rd, 1. 1 minus 1 is 0, so you have minus x to the power of 4, minus, now you put 0 for z, it is x minus 1 to the power of 4.
Hold up. Oh, he's just substituting. Suppose the matrix. Wait. Oh, hold on.
Minus, now I put 0 for z, it is x minus 1 to the power of 4. So this becomes 1 over
Oh, plus 1. Oh, that was for 0, okay.
72. Now minus on minus is plus. Oh, sorry, this is, yes, it is plus, but that is, look, this is from 0 to 1. So the first one is x plus 1 to the power of 4 dx. The second one is this and this, so it's twice. So 2 over 72 is 1 over 36. Then the integral is x to the power of 4 dx.
1 over 2. Oh, okay, already skipped like 5 stages there. No. This is the integral of 2 minus 2x cubed. He takes the 2 out by dividing the 2. Okay, and then he goes ahead and so this one is going to be in respect to x. So this one is going to be minus, and minus is a plus. This is going to be plus. Am I right in saying that? I think so, yeah. So plus. Did you know? Oh, it's minus. Okay, so it's plus 1 over 72.
And this goes from 0 to 1. And lastly, the third one, minus on minus is plus 1 over 72 integral from 0 to 1
X minus 1
x
to
minus 1 to the power of 5.
X.
Sorry, the power of 4.
Exactly.
To the power of 4 dx. So the
One
whole
step
lot
at a time.
becomes 1 over 72. You have x plus 1 to the power of 5 over 5. That's the first integral. The limits are from 0 to 1. The second one is 1 over 36 x to the 5/5 in limits 0 to 1. And the third one is 1/72 x minus 1 to the power of 5/5 in limits 0 to 1. And that is equal to 1/72. 1 plus 1 is 2. 2 to the power of 5 is 32. 32/5 minus 0 plus 1 minus 1/5 minus 1/36. Then you have times 32/5 times 32/5, and finally plus 1/72. Then when x is 1 is 0, and when x is 0 it is minus 1/5, so times minus minus plus 1/5. Right, so that will cancel that. The answer, if you simplify, you
1/72. 32/5. 32/5. What the fuck? 32/5 minus 1/36. 32. Good. Didn't give the right answer, man. Doesn't give the right answer. Holy shit. One plus one is 2. One 72. One plus one. Plus 1/72. One plus one. Actually, 0. So it's 0. Shift store A. So number 36. It's A minus A minus A plus C. 1 over 12. I did a mistake somewhere here. Anyway,
You again get
just technically
1 over 12. So this will be absolutely the same. So this is this example. Let me now give a definition for an elementary region. Okay, so this is the definition. An elementary region. Now, basically, bear in mind that the ideas that we encountered for functions of two variables, which lead into a three-dimensional space, now have to be trivially promoted to a four-dimensional space, despite the fact that we can't visualize that. So, as we had an elementary region in that space over the xy region, now in the two-dimensional section of the three-dimensional space for a function. So recall we had x simple and y simple region. So this is x and y, the two-dimensional section of the three-dimensional space where you plot the function of two variables. So depending on the shape in the xy plane, we had x simple, y simple region, and so what we'll do is generalize these ideas in one dimension higher, so an elementary region in the three-dimensional space So here we are talking about elementary region in a two-dimensional space of the three-dimensional space where the function of two variables is plotted. Now we are talking about elementary regions in the three-dimensional space, which is a section of the four-dimensional space where the function of three variables is plotted. So we're going one dimension up. So what is that? The elementary is the one defined by, let me use restricting one of the variables to be between two functions of the remaining variables. With the domains of these functions being elementary. That is x simple or y simple. Okay, so let's plot it so that we get an idea. Now we can't plot again, we can't plot the function, because to plot the function we need a fourth dimension. Here, for a function of two variables, it's fine. You need two dimensions where you plot the x and y axis, and along the third dimension you plot the functional values. Now, the x and y simple regions, here, the region of integration lived in a two-dimensional subspace of the three-dimensional space. Now, a region of integration is three-dimensional, which is a subspace of the four-dimensional space, where the function f of x, y, and z has been plotted. Think of the fourth axis being called w. Again, we can't see it, we can't imagine it. Okay, but what we know is that the region is either x simple or y simple. So this is along the x-axis. Think of a, b being the interval where x is allowed to vary. There. And then what we have is a function of x. Let me just and then another function of x. So this one here is phi 1. This one here is phi 2 of x. Okay, so this is an x simple region. So x varies simply between a and b, and y varies for every x between a and b. For example, that value there. Y will vary between phi 1 and phi 2. So should I say it this way? For every x between a and b, y varies between phi 1 of x and phi 2 of x. Okay, and then what we have are two functions. So let me, from these four corners, maybe I should use there. From these four corners, I'm going to up. So first of all, this is one of the functions. So you see this surface here. Let's call this surface z is gamma 1 of x and y. So this is a function which is built over that region there. And then there is another one. So this line continues. Get the picture. So this one here, that's the top. So this function is another function, gamma 2 of x and y. So for every x in between a and b, y varies between phi 1 of x and phi 2 of x, and z varies between gamma 1 and gamma 2. So gamma 2 of x and y, where this y here, actually this is where it varies between phi 1 of x and phi 2 of x, and at the bottom it's gamma 1 of x and y. So this here is how we are going to parameterize, is how we are going to call this region, right? How we're going to parameterize this elementary region. Now, likewise, if we have instead, if we have an y simple region, so let's sketch it, make a faster sketch of this one, x here, y there, z there, so we have c, d there, then we have the function x, which is psi 2 of y, then we have a function here. In this lecture we will revisit line or path integral. Okay, in the next lecture segment d there, then we have the function x, which is some function psi 2 of y, then we have a function here x, which is psi 1 of y. So here you can see that for every x, for every y between c and d, for every y between c and d, right, for instance this one, x will vary between the lower function and the upper function. And then how about z? Well, we simply, so this is c there. So we have two functions, one which is here, so z varies between this bottom and this top. Right, so z varies between these. So here I should say z is between the functions gamma, again gamma 1 and gamma 2, you can call these gamma 2 and gamma 1. So gamma 2 and gamma 1. So these are functions of, maybe I should write that. So, gamma 1 at the bottom of x, y less than or equal to z less than or equal to gamma 2 of x and y. So this is gamma 2 on top of x and y. On bottom you have gamma 1 of x and y. So you see, for every y between c and d, right, for every y there, x varies between the lower function psi 1 and the upper function psi 2, and then for every x and y from within that two-dimensional region, z varies between this surface, which is gamma 1, and this surface, which is gamma 2. So this is what is called an elementary region. And let me now describe the unit ball as an elementary region. So it's example 2 is to describe a unit ball. So this is a sphere of radius 1 to which the interior has been added. So this is the sphere of radius 1. If you add the interior, so you are less than or equal to, so all points that are on the surface, that's the equal sign, and on the inside of the sphere, that's the less than sign. Describe the unit ball as an elementary region. So, one possible solution, there are many possible solutions, of course, because you see x, y, and z enter on equal footing there. So they're all squared, and then they're added together. So whatever you say about x, you can say about y, you can say about z, for that reason. So one possible solution is the following one. We restrict the variable z between two functions of x and y, so that the domains of these two functions are y simple. They could be x simple as well, so that's like each of these possible cases has subcases, and each of the possible subcases is equivalent to all the rest. See, two functions of x and y, so that the domains of these two functions are y simple. Okay, so what would that mean? That would mean the following. Okay, let me draw the first of all. That's the origin. You have a unit ball, so that is ball centered at the origin O. So which means that in the xy plane you have a circle. So this is that ball. That. And that. So this is, maybe I should use different color. The yellow circle is the section of the ball with the xy plane. So xy plane has equation So what's common for all points on the xy plane? What's common is that z is equal to 0. So when z is equal to 0, x squared plus y squared plus z squared less than or equal to 1 becomes x squared plus y squared plus 0 is less than or equal to 1. So what is that? That is a circle of radius 1, the yellow circle, to which the interior has been added. So you have a disk. So we have a disk in the xy plane, and so clearly z will be varying between the the lower hemisphere and the upper hemisphere. So if I select this, so this is the lower hemisphere, and then you also have the upper one. So they're all stitched together, the green, the yellow, and the purple on that one, and as well at the back. Okay, so you have the function z varying between two functions of x and y. One of these functions is the lower hemisphere. So solve for that to see that. So you have, so look at the boundary first. So the boundary of the bow is the sphere x squared plus y squared plus z squared is equal to 1. Now solve for z. So what we have is z squared is 1 minus x squared minus y squared. Take square root, so you have z is plus or minus square root of 1 minus x squared minus y squared. So the upper hemisphere is z is plus the root. The lower hemisphere z is negative, so it's below the xy plane, that is minus the root. Okay, so these are the two functions that we referred to. So that would be, let me use different color for that one. That would be gamma 2 of x and y, and the green one here, the lower hemisphere, will be gamma 1 of x and y. So basically for every point inside the disk which is given by this equation, z varies between the lower hemisphere and the upper hemisphere. So, and that is the idea. Now we have to parameterize. The disk here. So I will erase this part because I don't want to write everything again on the new page. Here we say, what about, let me do an aside. Let us look at the circle from above, from the z-axis, so we're looking downward. So this is your x-axis, this is your y-axis. So what we're going to say is that for every y between minus 1 and 1, so this is this circle, the equation of the boundary, the equation of the circle is this. So I can solve for x. So x squared is 1 minus y squared. And if you take square root, so this is x is plus or minus square root of 1 minus y squared. Okay, so look, for every y between minus 1 and 1, so this is a circle here. So for example, if I take a value between minus 1 and 1, so if I take this one here, x will vary between this point and this point. So this semicircle and this semicircle have equations. One is with a minus sign, the other one is with the plus sign. Okay, so, and it is now very simple. For every y between minus 1 and 1, x will vary between 1 minus y squared, between this 1 minus y squared and this, and then z itself will vary between gamma 1, which is the lower hemisphere, and the upper hemisphere, which is the one with the plus sign, 1 minus x squared minus y squared. So this is the parameterization of that ball. And what I'm going to But of course, if you want, you can just open a bracket here, an additional one. So this is again the unit circle in the x, y plane, and here is -1, this is 1. So for every x between -1 and 1, so for example, if you take this value here, which is between -1 and 1, y will vary between the lower semicircle and the upper semicircle. Now, to find the equation of the upper semicircle, is you solve this for y. So this is 1 minus x squared with a plus, and the lower semicircle is clearly the same but with a minus. So the parameterization in this case, if you want to use that one, is as follows. I'll try to squeeze it here. For every x between -1 and 1, y varies between the lower semicircle, 1 minus x squared, and the upper semicircle, 1 minus x squared, and z varies between the lower hemisphere and the upper hemisphere. So this is z here, which is between the lower hemisphere, 1 minus x squared minus y squared, less than or equal to z, less than or equal to the upper hemisphere, which is 1 minus x squared minus y squared. This is just as before, as here. This is the same thing. So they're the two. So it's like with x simple and y simple regions. So what I'll do next is calculate the volume of the ball. So if I take f of x, y, z equal to 1, then integral of dx, dy, dz over that ball will be simple.
Why do you laugh?
dv over the ball, which will be v, which is the volume of the ball. So let's calculate the volume of the ball using the representations that we had. So
You should do it in 6 minutes.
over the ball b of dx, dy, dz is integral. Now, whichever one you want to use, I started with the yellow color, so let me use this one here. X is from -1 to 1, dx. Then y varies between the lower semicircle and the upper semicircle, and z varies between the lower hemisphere and the upper hemisphere. dz. So this is equal to integral from -1 to 1 over x, integral from -1 minus x squared to 1 minus x squared, and now over y, and now we integrate. Integral of the z is z. Z in these limits, so this is 1 minus x squared minus y squared, the upper one, and the lower one is 1 minus x squared minus y squared. 1 here and 1 there. So this is equal, so the square root minus the square root is twice this square root, 1 to 1 minus 1 to 1 dx, integral from there to there over y, and then we have the root, which is 1 minus x squared minus y squared dy. Right, so I've written dy at the back. Okay, so what's that integral here? That integral is, well, to solve that integral, you say let a, now we integrate over y, so this is a constant, let's call that constant, well, 1 minus square root 1 minus x squared, let us call that one a. So what we get then is the following. So with this our integral becomes twice, so with a identified as, so a squared is 1 minus x squared, so you have 2 from minus 1 to 1 dx from minus 1 minus x squared 1 minus x squared integral of a squared minus y squared. dy. And note that this is when I change 1 minus x squared, I forgot to change the limits. This limit becomes, this is 1 minus x squared, so this is equal to a, this is a, so it's minus a and a, so this is twice integral from minus 1 to 1 dx integral from minus a to a of a squared minus y squared dy. Now note that this here is equal to the area of semicircle region of radius a, right? And that semicircle of radius a is pi a squared, and because it's semicircle, that's over 2. So our integral becomes, so if I plug that in here, that's but with a now given by that. So let me continue on the page. So this is equal to twice integral from minus 1 to 1 integral of x pi a squared over 2. That's the area of the semicircle region. But note now that a squared is 1 minus x squared. So this is 2 over 2 is 1 integral from minus 1 to 1 pi outside. Then we have 1 minus x squared dx, and this is pi integral from minus 1 to 1 dx minus pi integral from minus 1 to 1 x squared dx. So the first one is pi x in limits from minus 1 to 1. The second one is pi x cubed over 3 in limits from minus 1 to 1. So this is pi 1 minus minus 1 minus pi 1 cubed over 3 minus minus 1 cubed over 3. So this is 2 pi, and this is 1/3 plus 1/3, 2/3, so it's minus 2/3 of pi. So 2 is 6 over 3, so it's 6 minus 6 4/3 pi. So 4 pi. Now recall that the ball of radius r has volume 4/3 pi r cubed, but because the radius is 1, we get 4/3 of pi. So this is the end of this lecture.
You can go to sleep. There's 1:30 minutes. We can finish this shit.
In this lecture, we will revisit line or path integrals, but this time we'll be considering line integrals or path integrals.
This is
So we call
almost
half
12
of
o'clock.
vector
We
field
finish at
f,
7
which is a function of x,
Okay.
y, z. This function f is actually not one but a set of 3 functions. The x component of f, which is x, y, z, a function of x, y, and z. The y component of f, which is also a function of x, y, and z, and the z component, which is a function of x, y, and z. Very often in mathematics, this first component is not written as fx, but simply as p of x, y, and z. This one here is labeled instead by q of x, y, and z, and this one respectively by r of x, y, and z. So in this sense, the function f, the vector function f, is the ordered triple of the three functions p, q, and r, each of which is a function of the three variables x, y, and z. So this is denoting the vector function f as an ordered triple. You can of course use the expansion with respect to the basis elements of the Cartesian coordinate system, the three-dimensional Cartesian coordinate system, namely I, j, and k. So you have q of x, y, z, j, that's the second basis element, and r of x, y, z, k, and this is the third one. Okay. Now, suppose we have a curve in three dimensions, x, y, z. Let me, just for completeness, draw the three basis vectors of the coordinate system. This is the vector k along the z-axis, the vector I along the x-axis, and the vector j along the y-axis. Suppose now we have a curve in three dimensions. So this is the curve. So let us call that curve C. Let us denote the general point on that curve by some letter, and the letter, because I've used P, I usually use P to denote the general point, P for point. Let us now use something else, so let's call this point M, and let that point be of coordinates x, y, and z. Now consider the vector which starts from the origin and terminates at point M. So let us denote this vector by r. Right, so r is nothing else but the vector OM, and this is xi plus yj plus zk, or simply the order triple x, y, z. So these are the components of the vector r, and respectively these are the coordinates of its endpoint M. Now, suppose that there is a parameter t, and as you change t, the point M moves along that curve. So that's what I'm trying to say here, is that we are going to introduce a parameterization of that curve. That is, we are going to write that x is a function of some parameter t, y is a function of the same parameter, and z is a function of that parameter. And as x, y, and z change, then the point M moves along the curve. So in this sense, the point M now becomes a moving point, so simply because these three here will be functions of time. So let me now rename that. So I'm going to get rid of M as a fixed point, and I'm going to replace that with the following. So the curve is also gone. Let me recover quickly what we have. So this is the curve C, and this is the point M on that curve. So point M has coordinates x of t, y of t, z of t. And as you vary t between t initial, or t1, and t2, then you single out all points from that curve between t1 and here t2. Okay, so in the same sense, r becomes now a function of time, simply because when you plug in the functions of the coordinates of n, which are functions of time, that becomes x of t I plus y of t j plus z of t k, or if you prefer to use order triples instead, this will be the set of the three functions x, y, and z parameterizing the curve C. So C is our curve, and this curve is given by the three simultaneous equations. Okay, now what we want to do is calculate the integral of the function f over or along the path C. So what we write, and that will be the line integral for vector field, and this is now a vector field, but we're not going to write fx, fy, fz, we're going to write p, q, and r instead. So let me erase that, I'll only maintain the drawing, right? And like this. So the definition then is the following. The line or path integral of the vector field f along C is denoted by C. Here you have f dot dr. Okay, so this is the elementary vector along that path. Recall how we introduced work by a force. That's exactly the work by the force, by the way. And this is integral, I'll show, from t1 to t2, because this is where t1 is. So we are interested in integrating along the path C only between t1 and t2. So that is where t1 is, and this is where t2 is. So this integral is over the path C, but only between t1 and t2. And this is then, the definition is f of r of t dot r prime of t dt. Now, this is rather obvious. Let me show you what is dr. dr r is a function of t, remember, from here. So dr is the same as dr of t, because r is a function of t. And recall that whenever you encounter the differential sign, if you want to bring functions in front of it, you have to differentiate them. So this is the derivative of r times dt. So that is that. Okay, now let me show you that from a slightly different perspective. So what we have is that f is the set of the functions p, q, and r. So each of these three is a function of the three variables x, y, z. And then if r is the vector of components, it's r of t, is the vector of components x of t, y of t, z of t, then dr, if you hit a vector by a scalar, it means that you have to hit each component of the vector by that scalar. Next I'm going to multiply and divide by dt, so this is equal to, now I'm going to multiply and divide by dt. dt over dt is 1, so nothing has changed, but this dt I'm going to plug inside, so that this will be dx of t dt, dy of t dt. So these are the derivatives of the functions here that parameterize the curve C. then you have dz of t dt, and let us not forget dt outside. This is the numerator here, which we left outside. That bit in the brackets is exactly r prime, the derivative of r. So f of r of t, what is meant by that is the following. We call that f is a function of x, of y, and z, and that is a vector. So for any point in your space, for any point x, y, z, you can calculate f. But we don't want to be off that path. We only need to know f along the path c. Namely, these functions here will, these arguments here will not be the arbitrary argument, the arbitrary point x, y, z, but these would be the arguments along the path. That is, we need only, just to squeeze that in here, so, we only need f where x is not just any x, but x of t, that is, x changes along this law, y changes along its respective law, and z changes along it according to its respective law. So this is then what is meant by f, the vector f of r of t, because r of t is the vector here. There it is here again, or here with the bracket we got, or here. Right, so that is what is meant, and this is now clear. And by the way, these integrals are extremely easy to deal with, and they look horrible, but they actually are a pleasure to work with. So, for example, if you
Thank
have,
fuck.
let me write again, so f is a vector field depending on x, y, and z, which is the ordered triple p of x, y, and z. So this is some function q of x, y, z, r of x, y, z. Right, so this is a set of 3 separate functions. Then the r is equal to, sorry, first of all, r, the path c, is characterized by the 3 simultaneous parametric equations. Recall how we did the helix. Okay, and then in that x, y, z coordinate system, the general point M from the path C between the initial and final value of time, t1 and t2 respectively, the general point M, which moves along the path as you vary t between t1 here and t2 there. So when t is t1, the point M is here. When t is t2, the point M is there. So that is the radius vector r of t, and r of t is the set of the 3 given, so these will all be given because the path C will be given. So r of t is the set of the 3 given functions x of t, y of t, and z of t. Thus the r, or rather let me just directly write r prime of t will simply be x dx dt dy dt dz dt. So therefore integral over the path C of f dot dr will be integral from time or t1 parameter. T is not necessarily time. From parameters value t1 to parameter value t2, that is from one end to the other, f of r of t dot r prime of t dt. And so what is f of r of t? This is equal to integral from t1 to t2. Now, this is the scalar product or the dot product of two vectors. Recall that if you have two vectors, A, the components of which are ax, ay, and az, and B, components of which are bx, by, bz, then the dot product of these two vectors is the product of the first components to which the product of the second components has been added, and the product of the third components has been added. So for that reason, I can write here, so we have the first component of f, which is p of x, y, z, with the first component of r, which is dx dt. Sorry, before I say that f is of r of t, so this is correct, but I should specify that this is x of t, y of t, z of t, and then we have dx of t dt, right? So, and then dt, because this is the first component of r prime, which we have here. This is the first component of f. So, and then we have plus, maybe I should write all of them together, plus q of x of t, y of t, z of t, multiplied, so this is the second component of f, that has to be multiplied by the second component of this, dy of t dt, plus the third component of f multiplied by the third component, just like here, the product of the third components. So that would be here, plus, we have plus r, x of t, y of t, z of t, dz of t dt, the whole lot dt. And this is extremely simple. Again, it looks bad, but it is actually extremely simple. Now, let me do an example. Consider the following problem. Example, and also pay attention to these examples because you might see them again. Example 1. Evaluate integral over c of f
Going
dr.
crazy.
So if you think of f as a gravitational force, for example, that would be the work done by the gravitational force for moving a particle along the path c. So where f is equal to f is a function of x, y, and z. Let me, if one is pedantic, there's nothing wrong with that. So f of x and y and z is equal to 8x squared y z I plus, well, clearly this is our function p. Let me immediately mark these. So this is our function p of x, y, and z plus 5zj 5zj. Now this here is our function q of x, y, and z. It turns out that q is a function, for this particular example, q is x squared. X is t, so you have t squared. Let me put this in brackets so that you see what's what. And y itself is t squared, and z is t cubed. So you see here that this is 8x squared of t, y of t, z of t, namely this. So when you plug in the functions which specify the curve, that means that you restrict your vector field f to a field along the curve only. Then you take the next one, 5z, so then you put the comma, 5 t cubed, that will be 5z, and then finally you plug in this one, minus 4xy, so it'll be minus 4, x is t, y is t squared. So let's see what we got. We got that the vector field f along the curve C only is this, t to the power of 2, 4, and 3 more 7, so 8 t to the 7, then 5 t to the power of 3, comma, minus 4 times t to the power of 3. So this is our f of r of t. So that is f restricted to the curve C. Okay, now what we also need is dr. Okay, so dr is simply r prime of t dt, right? Again, if you take stuff outside of the dash sign, you differentiate. So that's what has happened. So what is r dash? So r is this, t squared, t cubed. So that means that r dash of t is the vector which has components that are derivatives of these ones. So the derivative of t is 1, the derivative of t squared is 2t, the derivative of t cubed is 3t squared. So therefore this vector here is 1, 2t, 3t squared. Next we need this next we need the scalar product of these two vectors, because this is what the integral is. So you need the scalar product there. We need the scalar product of this vector and that vector. So let me erase perhaps somewhere here if I can, maybe we'll try this. So this integral over C of f dot dr is then integral from t from one end until the other. So these are the here t varies between 0 and 1. T varies between 0 and 1, and then you have the product of the first component of f with the product, so it is 8t to the power of 7 times 1 plus 5t cubed. Maybe I should put brackets so that let me put 8t to the power of 7 times 1. So this is the first component of f, this one, with the first component of for values of t between 0 and 1, and so 5 enters once there, twice there, so you have 2 times 1, so it is plus 2 minus 0, right? And then you have once there, twice there, so that is minus 2, so that the whole lot is 1. So this integral of this function f along the path c for values of t between 0 and 1, and c is given by, that is the parameterization, so t squared, t cubed, then this integral is equal to 1. Okay. Now, another type, example 2. With example, this is the same, rather. Example 2 is evaluate integral f and c is the line segment from point -1 what is the lines x, y, z? So we have a point x0, y0, z0, and we have a point x1, y1, z1. So these 2 points, let's say point, no, p and q are not good, m and n, points m and n are given. Now, what is the equation of the straight line that joins these 2 points? That's the question. There is only one such straight line. Right, now, look, I'm going to, well, the equation we're going to write in a parametric form. X as a function of time, y as a function of time, and z as a function of time. And these functions are to be determined. Now, if I tell you there is a straight line between point of given coordinates and another point with given coordinates, what is the equation of that straight line? Now here, the parameter t will run between something. Let us choose that t is equal to 0 at that point, and because the index here is 0, so let me say that t is equal to 0 at this point, and t is equal to 1 at this point. So we choose values t1 equal to 0 and values, so I should say and values, and t2 equal to 1 for the parameter t. So this is this parameter that is the argument of the functions x, y, and z. That is, as t varies between 0, varies continuously, between 0 and 1, all points from the segment n will be obtained. So you see, if t is 0, it means we are here. If t is 1, it means we are there. If t is between 0 and 1, it means we're somewhere in between. So what would be, just by looking at it and just by smelling it, what would be a good way to express this? So look, if we write x of t, we want x, so we want x to be x0 when t is equal to 0, and we want it to be x1 when t is equal to 1. So it's very simple to write it. Look, we want this to be x0 when t is equal to when t is equal to 0, we want it to be x0, so I'll write tx0 plus, and when t is equal to 1, so sorry, beg your pardon, when t is equal to 0, I'll write, and now I explain. I write here 1 minus t, and here I will write plus t. And now let's verify. When t is equal to 0, this term will be gone. When t is 0, 1 minus 0 is 1. So clearly when t is 0, x will be equal to x0. Now, if t is equal to 1, here in the brackets you have 1 minus 1, which is 0. Here you have 1. So when t is equal to 1, x will be equal to x1, which is at the other right. So that is our good representation. And in the same way, we write 1 minus t y0 plus t y1, and z of t as 1 minus t z0 plus t z1. Now, let us find the straight line that goes through the given points. So I'm going to erase this part. So this is so this is here x0, y0, z0. This here is x1.
Fucking dying.
This is y1, and this
Go to sleep.
z1. So x of t is equal to 1 minus t times x0, which is minus 1, plus t times x1, which is 3. So this here is minus 1 by minus 1 is plus 1. So t plus 3t, it is 4 times t, and we have minus 1. So let's verify. When t is 0, x is equal to minus 1. When t is 1, you have 4 times 1, 4 minus 1, 3. So perfect. Now, what is y of t? Similarly, 1 minus t.
Wait, what happened?
Then we put y0, which is 2, and then plus t times this one, which is 0. So that's what this is, minus 2t plus 2. Now let's verify. When t is 0, this is 0, y is 2. When t is 1, this is 2 minus 2 plus 2, 0. Fine. Now, z of t is 1 minus z times 2, oops, no, times 0, because z0 is 0, plus t times 1, like that. So this is simply t, and it's clear. When t is 0, z is 0. When t is 1, z is 1. So this is our curve, right, along which we have to, so r of t, which is the set x of t, y of t, z of t is the ordered triple, 4t minus 1 minus 2t plus 2t. Recall, we need the derivative. Thus, the derivative is equal to the derivative of 4t minus 1 is 4. The derivative of minus 2t plus 2 is minus 2. The derivative of t is 1. So that's not a surprise, because all functions are linear. Their derivatives are constants. It's perfectly within the range of normality. Okay, I mean, it's not, of course,
In the range of normality. Sorry,
Case,
am I in the range of normality?
No, the function f.
I don't think so.
Let's address the function f. The function f
I'm
is
actually waiting for it to end.
equal to xzi, and then you notice that there is no y, so I'll write simply plus 0 times j. There's no j, beg your pardon, so I'll write 0 times j. minus yz times k. So this is the ordered triple x z 0 minus y z. So this is f of x, y, and z. Maybe I should have written here not just f, but I should have written f of x, y, and z. Now, what we need is f restricted on C is f, where x is the set function x of t, which is this one, y is y of t, which is this one, and z is z of t, which is this one. Right? So that is, what is that function? So this is x times z. So this is 4t minus 1 multiplied by t. So this is xz. So this is x, this is z. Right? So this is, that is x, that is z. Right? Then we have 0, and then we have minus yz, minus 2t plus 2 multiplied by t. So let me open up all brackets. So this is equal to 4t squared minus t, comma 0, and then have minus on minus plus, so that will be 2t squared minus 2t minus 2t. Next we need what can I write?
Minus yz.
For a second, perhaps there is the parameterization. Because we've used that already. We found r dash. There, that is r dash. We found f of t. So what we then need next is very simple. It is just change the code, right there. So integral over the curve C of f dot dr is integral from t0, which is 0, sorry, from t1, which is 0, to t2, which is 1, f of r of t dot r prime of t dt. So we have to take the scalar product of these two vectors, so let me color code them. So f of r of t is this one, this with the first component, done. The second component of this times the second component of that, so that is 0 times minus 2, which is 0, but let me write it so that you can see what's what. And then finally the third component of f, which would be 2t squared minus 2t, multiplying the third component, and then you write dt. And now I do 0 to 1, so what we have is 16t squared minus 4 times t plus 2t squared minus 2t dt. And this is extremely simple. These are all table integrals, which you can do without problem. This will give you the following. The integral is was the limit here from 0 to 1. So this is integral from 0 to 1. So we have 16 plus 2, so it's 18. I take 18 outside brackets, and I have t squared dt from 0 to 1, and then minus 4 minus 2 is minus 6, which I take outside of the integral, from 0 to 1 of t squared dt. Now this integral is t cubed over 3 in limits from 0 to 1, so this is 1 cubed over 3 minus 0 cubed over 3, so this is 1/3. sorry, this is not t squared, it is just t. This integral is, because it is t, right? It's not t squared. This is equal to t squared over 2, a table integral in limit 0 to 1, which is 1 squared over 2 minus 0 squared over 2, and this is 1/2. So our whole, the full integral f, this one here, is therefore 18 multiplied by 1/3 minus 6 multiplied by 1/2. So this is 6 minus 3, and this is equal to 3. So as you can see, it is extremely simple. Now, we are not
Success!
finished yet with this. I will continue with a little bit more on
Is that finished?
path or line integrals of vector fields next week. So this is the end of this lecture.
Oh my god, I'm so happy. Hmm.